Hello, everyone. So today we're going to be talking about various concepts in petroleum engineering. My name is HUSSEIN KHORSHED. I have a bachelor's and a master's degree in petroleum engineering. The presentation will be 6 hours long, and we will be covering mainly just high-level topics that every petroleum engineering student or petroleum engineer should be familiar with. So first off, with the agenda, we'll do a quick introduction into petroleum engineering, the what, where, why, and how, and then we'll talk about hydrocarbons and define them. Then we'll move into petrophysics, which consists of rock properties and reservoir fluid properties and how they come together in gathering all the information that we need as a petroleum engineer to understand our reservoir. And then we'll move to the life cycle of a well, which is basically the step-by-step from start to finish of what to expect in a well, from exploration to drilling to logging to completions, then production engineering and reservoir engineering. All of these are different subfields of petroleum engineering that you can get into. And finally, we'll talk about petroleum economics, and that will conclude the first part of the lecture. So, the first question we want to ask is, what is petroleum engineering and what are hydrocarbons? Petroleum engineering is the field of engineering that applies science and technology to efficiently and safely extract oil and natural gas from underground reservoirs. So when we say oil, there are multiple different types of oil and also natural gas, which are both very economically profitable if you do them correctly and produce them correctly. And when we discuss a reservoir, think of it as a big tank of oil or natural gas that you're going to be working with that contains both the fluid and the source rock or the formation rock. So the question arises is, why study petroleum engineering, especially now? But in reality, there is a statistic that if we were to stop producing oil and gas, that it would take a few decades before we actually can make the final transition. But in reality is that petroleum engineering and oil and gas is here to stay for quite a bit of time. As of right now, there is a high demand for energy, obviously with the movements and the exponential growth in technology that requires energy, and due to the fact that there's not many alternatives as of now that can replace or fill the gap of oil and gas. So other sources of energy is that we have coal, then there's oil and gas, and then we have some renewables that have matured like sun or solar energy and windmills and so forth that count as renewable energies. But there's no sufficient enough or economically feasible possibilities to replace oil and gas just yet. One thing to note, though, is that with the oil and gas advancements in the past century, we can say that this industry has had the fastest pace in terms of cutting-edge technology. So when you're a petroleum engineer, you're exposed to some great technologies, and you have lots of hands-on engineering challenges that we'll see when we're looking in the life cycle of a well and the different subfields of petroleum engineering. But it's basically a very high-risk, high-reward type industry. And in reality is that the oil and gas industry itself are the ones driving the search for that replacement energy, for that renewable energy. So what we call the energy transition is from non-renewable to renewable. It is the oil and gas industry that's driving that change. So you would be part of that as well as a petroleum engineering student. And what people are finding actually in the renewable world is that lots of the tools and approaches the oil and gas industry takes to producing oil, there are similar methods or similar approaches or scientific concepts that apply to the renewable energy sources. So there's a lot of demand in petroleum engineering. It is a great field to study. It is still a very relevant field, and there are even more advancements now with when you talk about software and artificial intelligence. the petroleum engineering and the oil and gas industry is definitely taking strides in applying that as well. So, where does petroleum come from? When we say petroleum, we're kind of talking about all the different hydrocarbons, and we'll define that. But essentially, they come from mainly the Mesozoic era. I have both the Cenozoic era and the Mesozoic era due to the fact that there are some fossils that date back to the Paleogenic time and the Neogenic time. But basically, the gist of it is that it comes from millions and millions of years ago, 100 to 250 million years of a constant evolution in rocks, forming these fossil fuels, forming these oils and different gases. So if you put it into the timeline perspective, it's a few 100 million years old. And with respect to the ground, obviously that's very, very deep, right? So when we're talking about petroleum engineering, we're talking about something sort of in the blind, in the dark. It's a science. It's using physics and different technologies to navigate through thousands of feet under the ground. So a few cool facts is that there's a well drilled in the Caspian Sea as deep as 40,000 feet. So when you think of that and put that into perspective, is that you really need to have lots of great tools and great technology to be able to gather data and produce oil from such depths. So currently, where is the oil? This is a picture from Wikipedia, but these are proven oil reserves, and we'll get into what that means in the petroleum economics section. But basically, a proven oil reserve is a reserve that can be scientifically or probabilistically proven that it exists, and it is sort of validated by a bank for financial reasons, obviously, because it allows the oil company or the operator to start the project and to drill and to produce more oil. So the biggest producers of oil are mainly in the Middle East. There's some, obviously, in Russia. Russia's a big producer, and then there's other places throughout the land like the U.S., Canada, and other various countries in Latin America, with Venezuela being the number one producer or having the most reserves. So also one thing to note is having the most reserves does not necessarily mean you have the most oil. It just means that you could potentially or hypothetically have that many or that amount of barrels. And these are 1 million barrels for your reference. Okay, so moving on is that we want to define what hydrocarbons are, right? So hydrocarbons is an organic compound consisting of hydrogen and carbon. For those of you not familiar with the biochemistry, is that you have hydrogen has one valence electron, so you can attach you can attach 4 hydrogens to 1 carbon, and 6 to 2 carbons, and so forth. We'll see the nomenclature for the different hydrocarbons or the most common hydrocarbons in the next slide. But one thing to note is that hydrocarbons in their nature want to rise to the surface of the ground. So they want to go from all the way in the depths of the thousands of feet all the way to the top of the surface. And if there's nothing stopping them from doing so, they will be reaching the surface. And there are some parts, some deserts, where you can see like these oil bubbles nearing the surface. And obviously that's not economical or producible, but it sort of puts the physics into perspective that these hydrocarbons need to be trapped. And that brings us to the image we have here. This is a pretty standard schematic diagram explaining that oil basically has to be trapped, or your hydrocarbon must be trapped in some sort of cap rock or something like that. And usually you do see this combination of gas, water, and oil when you do find oil. So it's you find these 3 fluids basically, and this diagram is depicting that. But the most important thing to note is that it is trapped somewhere. So as a petroleum engineer, your objective is to remove it from that trap and produce it in an economic and profitable way. And whenever we talk about anything or any objective of a petroleum engineer, there is this economic factor or this economic parameter that we want to assign to all our objectives, right? We need to make money at the end of the day. If something is not feasible, we will not be able to produce. Okay, so the different examples of hydrocarbons is the most common is CH4, like we mentioned earlier. That's methane. It's the main component in natural gas. It's the most abundant. We have ethane, C2H6, propane, C3H8, butane, C4H10, and pentane, C5H12. If you're not familiar with organic chemistry, you can draw it out and kind of basically draw C and 4 carbons around it. If you draw 2, you would have 6, and so forth. And that's where the simple organic structure comes from, right? And when you add a carbon, sort of, you're changing the nature of the fluid density, the gravity or API gravity of that oil, right? Lots of these you should be familiar with or you've seen before. So butane, for example, is in lighters or when you're doing barbecue. Pentane is really important for gasoline production, right? And it's one of the lighter hydrocarbons. So with that introduction, we can step right into basically the first fundamental concept that we want to know as petroleum engineers, which is fluid properties and rock properties, right? And it's basically the petrophysical properties that we need to understand to be able to produce the oil. So in order for us to optimize production, we need to basically understand what we're working with here, right? So what surrounds the oil? What is the nature of the oil? What are the different rocks around this oil? And what does our reservoir look like? What's the pressure, the temperature, and so forth? Because the more we understand our reservoir, the better we can optimize our production. So let's start with the bigger bulk of the two, but essentially lots of these concepts overlap, and some of these properties belong to both the rock and fluid, as we'll see. But when I talk about rock properties, I'm talking about the connectivity due to the rock structure or the formation structure, the porosity, which we'll define, but it's basically the space within a given medium for rocks, and the trap or the nature of the trap and what's trapping the oil reservoir, right? So it's not always clear cut. You have different formations. You can have more than one type of rock, more than one type of density. You can have more than one type of fluid, right? So starting with porosity, right? So porosity is a relatively easy concept to understand, but it is a bit counterintuitive when it comes to defining it or trying to solve for it. But essentially, the porosity is the volume of the pore space with respect to the total volume. Now, what is the total volume? It's arbitrary. It's for you to define. And that's why porosity is only relative to the spatial geometry, as in you must define the geometric shape that you want to look at and solve for the porosity there. And in the application side, this is usually done with core samples, and we can get into that later, but essentially you're just taking a small piece of the formation rock from downhole, and then you bring it back up and you take it to a lab to analyze its porosity. We have a diagram here displayed, and this sort of captures what we're talking about when it's relative to the spatial geometry, is that in the leftmost part of the diagram where it says non-porous and non-permeable, it's a bunch of rocks put together. There's not many pathways or like these blue pathways that you see in the other parts of the schematic where fluid could flow through. So we call this non-porous. If we put water, it wouldn't go through these rocks, right? And in the middle, we have this porous non-permeable, which is an example of where there are some little holes, but there's not much connectivity. So if we were to push a fluid, maybe it will fall into some of these holes and get trapped, but we wouldn't be able to push the fluid from start to finish or from the one line to the other line. And then finally we have this porous and permeable, where you can see this connectivity between the blue color. There's lots of space. The rocks are big, so fluids can easily pass through these little capillary complex systems, right? And if we were to redraw those red lines, so if I took two of the first left two, so the non-porous and the porous, and combined it together and calculated that porosity, that would give me a different number than if I had taken one individually and so forth, right? So it's important to notice that it is based on what you define as the space that you want to look at to define the porosity. Now, Porosity, one thing to note, mathematically, it is dimensionless, which tells us that we can sort of solve for it through other manners, right? Through another approach, or we can use this porosity value in multiple of our equations mathematically, and we don't mess with the dimensions. So it becomes very beneficial for us to have this dimensionless value. And in petroleum engineering in general, or in physics in general, physicists like to make things simple. So when we make things dimensionless, it gives us more freedom and flexibility. One example of this freedom and flexibility that we can talk about here is one way to calculate the porosity is through, since it's with respect to volume, is you can calculate it with respect to density. And that's sort of what Archimedes came up with. So Archimedes was a historical physicist in Greece a long time ago, and the story goes is that the king received a present or a gift from some foreign entity, and the king wasn't sure if that gift of gold was accurately gold or was it fake or so forth. So he asked Archimedes, can you validate to me if this is real gold or not? And Archimedes thought about it for a long time and wasn't able to validate it, basically. And the story is that his wife tells him, okay, go relax, take a bath. And when he goes in and takes a bath, he notices the displacement of water, right? So that displacement in water is relative to the change in volume. And the change in volume, well, we know that like the density by definition is mass over volume, right? And so now I can relate volume to density, and I know the density of gold. So he was able to relate the density of gold through solving mathematically for density with respect to the displacement and volume. Now, petroleum engineers took that approach and basically used the densities to solve for porosity. So that's just an idea of a cool way that petroleum engineers have to think to solve problems, right? So this is a very important term that you should be very familiar with. And permeability is almost equivalently as important. The definition of it is the ability for a fluid to flow through a porous medium. Now, when you look at that definition and you think about it for a while, well, it could be a property of the rock, and it could also be a property of the fluid, right? There are different types or subtypes of permeability that we will define in the next few slides, and we will kind of clear that up. But that's actually a philosophical question, more like what permeability is a property of it. Is it a property of the rock or the fluid, right? But whenever we talk about permeability, we usually use the term Darcy's, right? Darcy's is the unit for permeability. So when we talk about Darcy's, we must understand Darcy's equation. And it's in its simplest form. It is basically this displayed here. Before we touch on the parameters, a little background on Darcy. Darcy was a French physicist, and he had nothing to do with petroleum engineering, but he worked with water irrigation systems, and he was trying to optimize his pipes basically whenever there was sand or mud that would fall due to weather or corrosion or whatever into his pipes, and he wanted to measure the rate of which water can flow depending on the different viscosities or different substances available, which is very similar to what a petroleum engineer is basically trying to do, right? They have their well and they have a fluid and they're trying to move that fluid as fast as possible with all its obstructions. So Darcy came up with this equation. It is Q is basically the flow over the area, which is equal to K, the permeability, which is the Darcy unit, divided by the viscosity, so the viscosity of the fluid we're talking about, multiplied by a pressure gradient. So pressure gradient is just the change in pressure over length, right? Over some sort of defined length. And that can tell us about the flow and the nature of its fluid, the permeability. One thing to note here is that this is actually, if you break it down in its most simplest form, fluid mathematically can only move, right? The flow Q can only have a number greater than 0 if the change in pressure exists. So the delta must be greater than 0. And that is something easy to understand. It's relatively intuitive. You've played around with it as a kid when you had a straw with some liquid and you put your thumb there. You're kind of negating the pressure, and that's why it stays and it doesn't fall. You're not defying gravity. You're just basically applying Darcy's law of making that delta P close to zero. Okay, so this is one of the most important equations. This is in its simplest forms. Obviously, when you get into the mathematics of it and the application of it, there's a lot of different derivations. For example, one thing to know is that we're talking about a pipe, so that length would change into some sort of radius multiplied by a pipe. We're talking about like a cylinder. So this is a very basic type of the equation. There are lots of different derivations, lots of different modifications to it to make it more applicable and more realistic when you're trying to calculate either the flow or the permeability of a fluid. So when we talk about permeability, there are three types or subcategories of permeability that we must know or we must define. So there's the absolute permeability, the effective permeability, and the relative permeability. These are all relatively self-explanatory, right? But when we talk about absolute permeability, we are talking about one fluid going through a porous medium and it's fully saturated with that fluid. So that tells us the exact or the absolute permeability with respect to the rock. So this is kind of sort of more related to a property of the rock, not the fluid, because through the fluid permeability, it will tell us things like size, shape, and connectivity of that rock. And you measure that usually with one fluid, and it has the symbol K, and it also has the units of Darcy's, right? And whenever we talk about Darcy's, in reality, when we're looking in the oil and gas world, we're talking about millidarcy's. So that's just one thing to know. Moving on to effective permeability. The effective permeability is when there are multiple fluids. So this is more about the realistic situation of what we work with as petroleum engineers. So it's with multiple fluids are present in a given pore space, and it depends on the fluid distribution and saturation levels. And we'll see how those are related later on when we're talking about fluid properties. But it is always less than the absolute permeability, which sort of makes sense intuitively, is that you must add all three relative permeabilities for the absolute permeability. So it becomes sort of a fraction. So if you want to know like the oil relative permeability, the water relative permeability, and the gas relative permeability, and they're all denoted as KO, KW, KG. Right? And finally, we have the relative permeability, which is just taking your effective permeability and dividing it by your absolute permeability, giving you that dimensionless fraction. So again, we're seeing this dimensionless ratio, which allows us to relate things that are not relatable through physics, but they're relatable through the reality or the nature of the thing we're looking at, right? So if I have this dimensionless permeability, I can relate it to saturation percentage, right? Because now it becomes a ratio, and the saturation within a given pore space is also a fraction, right? So this is fundamental for multi-phase flow modeling and reservoir simulation and other things like water flooding behavior. But basically, it's just when you're trying to understand how different types of fluids, or the three main fluids that we work with, oil, water, and gas, are behaving with respect to the rock. Another important term is wetting or wettability, and this talks about basically surface tension and interfacial tension, but it is a property of both the rock and fluids, and it is how a fluid distributes itself against a solid surface. And there's this arbitrary categorization where we say something is water wet if the degree between the surface and the fluid is less than 90, and it's oil wet if it's greater than 90, right? And if you want to think about this in terms of a simple or more applicable aspect, you will also see a drawing of it when we're talking about capillarity, but is mercury. If I drop water on my table, it will sort of spread out naturally, right? Whereas if I drop mercury, it will sort of form this ball, and it's kind of resisting the touch of the wood, right? It wants to touch as minimally as possible, where water wants to kind of spread throughout the surface. So that is what wettability is, and it becomes very important because when we talk about wettability and we're talking about capillarity, that's kind of defining the connectivity that we have in our given pore medium, right? So the capillarity is the interconnected reservoir which forms a complex capillary system, and in reality they do. You have big pores, and then you have the small channels in a pore space or medium when it comes to oil and gas, and you want to be able to understand the different types. So you want to understand how the water flows through big spaces, through small spaces, what gets stuck, what is able to be pushed forward, right? What can we actually produce from that given space? It's never 100%, and we'll see why in the next few definitions. But also another cool thing when it comes to physics here is that we're talking about capillary action, right? So when we're talking about capillary, this diagram shows something relatively cool because, again, when we think of capillary pressure, we think, first of all, pressure by dimensions is some sort of force over area, right? And what capillary pressure is rewriting the equations for pressure in terms of height and density. So density, so rho gh basically, so density times gravity times the displacement or the delta in height will tell us about the pressure. Now, you can see obviously how important that is with respect to when you're drilling a few thousand feet into a well, and pressure is one of the most important parameters you need to know, and that displacement and height will tell you a lot about the density of the oil and how fast it's going to flow and what's the change in pressure, right? So that's the pressure gradient again. So since pressure sort of defines the movement of fluids, pressure is usually one of the most important parameters that we're working at. So the reservoir pressure, surface pressure, the wellbore pressure, all of these things will dictate how well we're able to produce or how little we're able to produce, right? But with respect to the rock is that now we have this, we know the wettability of the rock, we know the capillarity of the rock, and now we must define two other terms that will also tell us about the movement of the fluid within the rock. And the irreducible water saturation is basically the lowest saturation that could be achieved by the displacement occurs when the wetting phase becomes discontinuous. Because the wetting phase naturally tends to remain continuous, there will always be an irreducible and residual water saturation. This is the saturation level that cannot be reduced any further by displacing it with a non-wetting phase, regardless of how much pressure is applied. That's a lot for a term, not for a definition, but essentially it's what this diagram shows is that you can push fluid as much as you want, but at some point there will be this irreducible point where it will not be able to move for water. So the water will kind of be stuck on these tops of the grains or the rocks or sizer as you see here in the picture. It's that you're pushing it and you're pushing, but at some point, no matter how much you push, there will no more water will basically come out, right? And since we have this definition for water, we also have a similar definition for oil that follows the same concept. So it's called the residual oil. And water tends to displace oil in like a piston-like manner, and this is the displacement order is sort of sequential, you can say, but at some point, as the displacement continues, the interfacial tension eventually breaks the remaining oil threads, leaving behind isolated droplets of residual oil tapped in the narrow pores, right? So it's kind of the same exact concept as the irreducible water saturation, but it's on the other side when we're talking about oil. And now we have this concept, right, is that we have this limit on water, we have this limit on oil, and we have the water saturations, which we said are relative or percentage-like, which means that we can bring this all together, right, into the permeability and fluid saturation. And this is where we want to relate the effective permeability literally becomes a function of saturation. And now when you have one, you can solve for the other, and vice versa. And this diagram is showing that is basically here on the left side you have the irreducible water region, on the right side you have the residual oil region, and in between when it's a water wet rock is that you have the relative permeabilities of the oil and the water, right? And on the bottom here, since water saturation is a percentage, you have the range that goes from the saturation of the water contact to the saturation of basically 1 minus the saturation of the oil, right? So this pretty cool graph is very important for reservoir fluids, and when you're trying to understand the fluid properties, which puts us into the introduction of all our different fluid properties, right? So here, this is just the high level top 5 categories of oil that you can look at. These are kind of again, they're arbitrarily defined, and basically it's a spectrum of different types of oils, and they kind of slice it up into these 5 categories. And you can see from the graph that there's a lot of overlap within each one. But you have black oil, volatile oil, retrograde condensate, and wet gas and dry gas, right? And here you can see in the graph is that there's this what we call a PT diagram, where you have the pressure on the y-axis going up and the fluid temperature on the x-axis. And we're about to define what all of these are. But again, when we're talking about fluids, we are talking about the thing that should be going through your head is basically PV equals nRT, but in petroleum we use a lot of different modifications of that. That's the ideal gas law, right? But if you break it down as to PV equals T, right? In your head is that if pressure goes up and temperature is the same, then volume must go down, and so forth. So as a petroleum engineer, you should always think about the relationship with pressure, volume, and temperature, right? So pressure and volume are inversely related, whereas pressure and volume and temperature, or pressure and temperature or volume and temperature, are proportionally related. So when we want to break down this PT diagram, and we want to understand what the graph means, the first point that we want to note, so this is an example in the diagram of black oil. In the previous diagram, we saw 5 different oils, but we're just looking at here to understand the namings and the labeling of this diagram. So you have pressure on the y-axis, temperature on the x-axis. Your point in your reservoir is at the highest pressure. So because when you drill a reservoir in its nature, let's say we'll start at 4,000 psi. Once you drill, naturally through the primary drainage of that reservoir, well, as you're decreasing the volume of the reservoir, right, the pressure is decreasing. The pressure will continue to decrease for the life cycle of a reservoir when you're trying to produce, right? So when we're looking at these graphs, we're starting at the top and we're moving to the bottom. So the point 1, 2, 3 kind of sorts of explain that. But let's go through the definitions. So the bubble point is the pressure where the first gas bubble comes out of a solution as the pressure drops. So you can see that at point 2, basically. That's the bubble point line. And then the dew point is the pressure when the first liquid droplets form as gas condenses. So it's kind of the other side of that envelope. Now the two-phase region is what we're working with lots of the time, right? In the petroleum world or in the production engineering world, that's kind of where you're at, right? Is this two-phase region, and it's the area between the bubble point and the dew point. You can see this dew point goes all the way to the bottom here, so that's the dew point line, and this is the bubble point line. And all the multiple smaller lines in between is the between percentage from you can think of it as two-phase, so gas or liquid or so forth. So where both of them coexist in that given environment, right? The critical point is the point where liquid and gas phase become indistinguishable and where the curves meet. You can actually search on YouTube to see what a fluid looks like. When I say fluid, it could be gas or liquid, right? And you can see at the critical point what a fluid will look like. When it reaches that, it's kind of a mixture of both. It doesn't look like a gas and it doesn't look like a liquid. It's this really interesting picture. You can search it if you haven't seen it before, but it's basically, it exists at that critical point. And then you have a single phase liquid region. So since we're thinking of this big little oval shape here as the two-phase region, obviously when we're in point 1 or to the top of this diagram at very high pressure, we're one single phase. So we're like high pressure, low temperature, which is the area left of the bubble point, and that's the liquid region, right? We're still a liquid here, and then under the dew point, where we're at very high temperature and lower pressures, you can say is that you become a single phase gas region. So this is pretty cool because it's explaining for the given single black oil in its journey from reservoir to throughout its period of drainage and so forth and production, is that it will continue to kind of evolve and change, and we have to understand how that changes, right? And not just under the ground, but also at the surface. Because think about it, when you have 4,000 psi and then you go to 1 atmospheric pressure, 14 psi, you're obviously, that oil will expand relatively drastically, and that's why there's a whole industry of midstream and downstream, which are solely focusing on how to transport the oil you produce, or the hydrocarbons you produce, and then how to refine them, right? These are two massive industries. When we talk about petroleum engineering, usually we're talking about the upstream side, so producing the oil from ground up, and then midstream is taking it from the ground through the pipelines to the refineries, and finally downstream are refining those hydrocarbons and making them accessible to the world, basically to society, right? So the top, or lots of the concepts that we want to know when we're talking about fluid properties are these listed below here. So the oil compressibility, the saturation pressure, the oil formation volume factor, the gas-oil ratio, liberated gas formation volume factor, incremental liberated gas gravity, and the cumulative liberated gas gravity. So these are different fluid properties that you should be familiar with, and we're going to go into defining each one from a high level, so just its definition, and if there's an equation associated with it, we will also define that equation. So the oil compressibility is the fractional change in oil volume per unit change in pressure. So you can see this equation, but basically it's describing how the oil volume decreases as reservoir pressure increases. So in our head, we just said that we have all this oil thousands of feet below, and then we bring it to surface pressure, it obviously will expand drastically. So the oil compressibility is talking about, it's the inverse direction, but it's telling you the same thing, right? This is a pretty important concept, or pretty important thing that we must know about our oil, because it will tell us a lot on how we need to operate. So the equation is denoted by C subscript O, which is the oil compressibility, and it's negative 1 over volume, so it's inversely proportional to the volume multiplied by the differential. Saturation pressure. So the saturation pressure is the pressure at which gas first comes out of the solution from the oil. So this is usually the bubble point when we're talking about black oil, or it first condenses from the dew point, so if for the lighter oils. So for reservoir oils, we're relatively talking about the bubble point pressure, right? So in those PT diagrams, that's what we were talking about. You saw the line, it sort of goes from 1, 2 to 3, and it doesn't touch the dew point line, right? Generally, the oil is just with respect to the bubble point pressure, sorry. The oil formation volume factor is the oil formation factor, which is the ratio of the volume of oil with dissolved gas at reservoir conditions to the volume of oil at standard surface conditions, right? So again, we find a dimensionless value, right, that we can use to understand the nature of the oil with respect to surface, with respect to the reservoir. And it accounts for the dissolved gas and oil shrinkage when brought to surface. So again, we're trying to understand how our fluid behaves. And when we say that we want to understand how our fluid behaves, we want to understand it both at the reservoir, at reservoir conditions, in production conditions, and at surface conditions, and through the evolution of your project life cycle of when you're producing the oil, and we want to understand that as well, right? And if we're going to understand oil, we must understand gas, right? Water is pretty easy to figure out, I guess. So mathematically or with respect to physics, the problems at hand are generally the oil and gas, and we're trying to define those as much as possible, right? So the gas-oil ratio, or GOR, it's referred to as GOR most of the time, is again another dimensionless uh, dimensionless field, but in the sense that it is dimensionless, it's volume over all volume, but it's usually said in these units, so pay attention to that, is the fact that it's square cubic feet per barrel, basically, right? So it's the amount of gas produced at standard conditions per unit volume of oil produced at standard conditions. So here we're looking only at standard conditions, and in physics or in math, when we say standard conditions, we're referring to atmospheric pressure, I think it's 22 degrees Celsius, and so forth. So when you're thinking of that, also when we're talking about standard conditions, it's respect to like that ideal gas law equation, right? So the pressure is standard, so 1 atmosphere or 14.67 psi. We're talking about 22 degrees Fahrenheit, Celsius, and that's like the world we call standard, right? It's this universal term. Now the solution GOR, it's the exact same concept, but it is at the reservoir conditions, and the producing GOR is the actual gas produced with the oil. So again, these are different ratios that help us understand our fluid and help us optimize or maximize our production. When we say optimizing oil and gas production, we are essentially wanting to maximize it, right? Because the more we produce, the more money we make. And this is a very money-driven project, right? As we will see in the economics of oil and gas. Moving forward to the liberated gas formation volume factor, that is the ratio of the volume of free gas at a reservoir conditions to its volume at standard conditions. So Bg is equal to the volume gas at reservoir over the volume gas at surface. So this shows us how much gas expands moving from the reservoir to the surface. And now we can move on to the incremental liberated gas gravity. Here, when we're talking gravity, we're talking API gravity, and it's basically the specific gravity, right, of the oil, and it's the gas that is released during a specific pressure drop interval, and it's measured for each step of pressure reduction. So this is usually done incrementally, and it allows us to define or characterize or describe how the gas composition changes over pressure declines. So over time, how is our gas behaving with this change in pressure, right? With this change in time. And finally, we can go to the cumulative liberated gas gravity, and that is the overall API of all gas released from the oil up to a given pressure. It represents the average composition of all liberated gas, and it is used in PVT analysis to track how gas quality evolves, right? So in summary, you kind of need all these properties of a fluid and the properties of a rock, and they're sorts of dynamic in the sense that throughout the life cycle of a well or the life cycle of a field that you're working with or working in, is that these measurements are not absolute, right? And these measurements you have to continuously, some of them you have to continuously take, some of them change due to the fact that the pressure is changing or the nature of the reservoir is changing. So this affects the drainage, it affects the production, it affects lots of things, right? So what we're going to see in our next, part is how all these different properties are acquired, right? So like we said in the beginning, these hydrocarbons and these reservoirs exist thousands of feet under the ground. It's not like space for example, space physics or astrophysics, where you can kind of see lots of what you're doing, and like they went to the moon in the 60s or so forth. You could, it's still very hard and complicated, but you can see lots of it up until a certain point. When you're in other fields that contain engineering, like mechanical engineering, chemical engineering, you can see, even on the atomic level, you can see what you're doing, right? Whereas in petroleum engineering, you cannot see anything, right? You're thousands of feet under the ground. But what you do is that you're trying to paint a picture. When you're trying to understand your reservoir, you're trying to paint a picture step by step. You're trying to acquire as much data as possible and make the best possible decision, as engineers do, based with the data that you have. And it's very interesting on how many advancements or how much advancements have taken place due to with an industry that is basically working in the dark, right? And what is cool about the petroleum industry is the adaptability of technology, right? So that we are able to use nuclear tools, sonic tools, to acquire or draw this picture that we're looking for to understand the rock. We can relate Archimedes' principle from, a Greek physicist from so many years ago or so many centuries ago, to relate that displacement in volume to be the displacement in density and relate that to porosity. And that tells us about our sandstone that we're trying to produce oil out of, where we take Einstein's photoelectric effect and we use that to also in our tools to be able to acquire more information again. For example, we'll see in some wireline tools where we're using a weird or very interesting amount of technology or discoveries in physics from different parts of the industry or just from the physics industry, and we're using that in a relatively creative and very innovative way, right? So that's something to keep in mind, and we'll get to see those applications now when we're talking about the life cycle of a well, right? So the life cycle of a well is we're going to take the journey of one well, right, until we kind of reach the production engineering and reservoir engineering. But we're going to take the journey of one well and how that well is sort of drilled in a given project. And we're going to see each well that an operator drills basically or makes or goes through similar life cycles, right? And there are different scenarios that we will see. But just before we start, a general background on when I say operator, right? Generally, you have, for example, a rig platform. There's a rig company that provides those and transports those, and they transport it to there's a rig facility, and then there's operators, which are companies like Shell or BP or Exxon, and then there are service companies. So the operators tend to generally, most of the time, they own the oil, right? So they're producing the oil and they own the oil. But what they will use are service companies. So service companies are like Schlumberger or Halliburton or Baker Hughes or Weatherford. These are oil service companies who provide the tools and technologies to these operating companies to produce the oil. But they generally don't own the oil. So for a service company, their customer is the operator, right? And these are just basically the different parties at hand for a given well. So before we start that, so moving forward, so we're going to go into all of these fields: exploration, drilling, logging, completions, and then production and reservoir engineering, right? And we're going in this order because this is kind of the order that the life journey of a well would go through. So it's the sequential order. In reality, there is some overlap and there's some back and forth, but we're not going to get into that. We're just going to assume this very linear path for a given well. So in the beginning, we have exploration, right? At this point, we know nothing, and we're trying to understand, or we're trying to find where's the best part of the ground where we can drill and produce oil, essentially. So what people usually do is that they start sending out these seismic surveys, and what that is, it's kind of interesting. Basically, you're taking a tool where you're you shoot out like waves, different waves, and you're measuring the return of those waves. And this allows those surveys for geologists and geophysicists to kind of build and structure their models, right, as we'll see. And then you move into identifying your prospects and leads. And then whenever there's oil and gas, there is risk and uncertainty. So here, one of the most important risk analysis are done, and then they can start the final phase of exploration, but it's kind of the starting phase of that life of a reservoir or the life cycle of a well, where you're exploration well planning, right? So we're going to define each one of these one by one. So seismic surveys are basically how we see underground without drilling, right? Without big investment, without throwing a lot of money at this project. We want to understand, is there a potential of proven reserves that we can produce, right? So like I mentioned, they use sound waves to map the subsurface rock layers. So you're essentially able to draw this very light picture, you can say. If we're thinking in terms of a painting and we're talking about the life cycle of a well, this is basically you just drew like the grids on a paper and you started very lightly tracing whatever you're about to paint. And what they do is that they have these big air guns, and they can do this on land or even on sea with these big boats that do the same thing. And there's this receiver attached to it, and they shoot out these waves into the ground, and they measure how long it takes for it to kind of come back. And based on that, they understand things about or properties of the rock from the top and a bit under, right? Because the waves will naturally respond differently or reflect differently on different rock layers, and they're captured by these sensors or receivers, you can say. And with that, the geologists and geophysicists are able to start creating this geological model, right? It's like your first set where you create these 2D and 3D images of showing structural traps, faults, and potential reservoirs. And remember, as our hydrocarbons are generally trapped somewhere, that's what they're looking for, right? That's essentially, they're trying to identify areas that would have potentially some hydrocarbon reservoir there, right? Before we want to drill an expensive well, or before we want to invest a lot of our money, we want to place our bets in a more probable scenario, right? In our best case scenario. So that's what a seismic survey is for. Obviously, it still is relatively expensive, but it's nowhere near as expensive as just drilling in the dark and hoping for the best to find your oil, right? So you're trying to identify that trap. So once you've done your surveys, the geologists and the geophysicists they kind of work together to create basically they study the surface rocks, the stratigraphy, the depositional systems, and fault patterns. If you're not familiar with these terms, like a stratigraphic map is sort of like those maps with like circles to show the depths, and you can search one if you want to see what it looks like. But essentially, geophysicists integrate the seismic, gravity, magnetic, and well data to construct subsurface models. And these are equally important, and together the geologists and the geophysicists will kind of build the first map we need. So they're called basin maps, and the cross sections and structural stratigraphic frameworks. And from there, they can kind of work together, and it will tell us more about our reservoir. So it's kind of shaping the outline of that reservoir. How big is it? Its thickness and quality and so forth. And the output of this mapping is that the geologists or the geophysicists will be able to create a geological model. So when we say so just to define, a geologist studies rocks, right? The properties of rocks, how much they've aged. They can understand how the rocks arrived at what they're doing or why they look the way they are and so forth. Whereas a geophysicist is understanding more about the physics aspect of it. So similar to like a biologist versus a chemist, you can think of it. But they're equally important. Their knowledge is equally important to the life cycle of a well. And these are two different fields that even petroleum engineers can get into lots of the time. So even though you can study geophysics in university and you can study geology in university, but petroleum engineers generally have a great understanding of lots of geology and geophysics. More geophysics than geology, but there should be a familiarity with geology. So once you have your model, let's say your geological model, the next thing is to identify prospects. And what that means is you want to, when you first are about to drill in your given reservoir, right, or in your field, you don't know where to drill. So let's say you have this big reservoir, right? You want to kind of optimally select some drilling or exploration drilling, basically, where you want to select these different parts of the reservoir or the hypothesized reservoir to know as much as possible, right? So you don't want to, for example, drill if you were going to explore with 4 wells, you don't want to drill 4 wells in the same location. That tells you nothing about the connectivity. That doesn't tell you anything about properties of the reservoir as a whole, right? So there's a whole strategy, there is a whole science, there is a whole field that goes into optimally selecting what's the best drilling targets, you can say. And this is where you're identifying prospects. So let's define these terms here. So a lead is an early stage idea based on a seismic or a geological model, or the clues that they're kind of gathered, or the data they were able to acquire, right? And a prospect is a fully evaluated drillable target which defines structure and estimated volume. So a prospect is basically what we just discussed, is that, okay, for these 5 wells, I'm going to drill these 5 wells in these specific locations to be able to gather more data and more information about my reservoir, right? So I can optimize my production for the life cycle of the reservoir. And when I say life cycle of the reservoir, it's not the life cycle of well, it's the collection of wells that are going to produce from the reservoir over time. And to put things into perspective, for example, there were a few wells in the Permian Basin, right? The Permian Basin is in West Texas. Before World War II. There were lots of drilling took place post World War II in the 50s, right? And up until now, the Permian Basin is one of the biggest reservoirs and oil producers, right, out there. So that puts things into perspective. When you're talking about the life cycle of a reservoir, it's this 50 to 60 or 60 plus or more than that years of a project, right? Whereas the well life cycle might be that long or might be a lot less. It depends, right, on the well itself. And we'll see why in the next categories or subcategories that we're going to talk about. But basically, back to the prospect is we know exactly where we're going to drill, and now this is the goal of identifying the prospect, is that we must estimate the trap size, the reservoir properties, the fluid type, and potential reserves. So ranking prospects helps companies decide where to drill first for maximum success. And this is what we basically discussed, but we want to optimize that selection. We want to, wherever we're going to drill our prospects must be placed strategically for us to optimize production. It is extremely important, right? But at this point in time, you don't know a lot. You haven't drilled a single well. You're still kind of working in the dark. So the risk is extremely high, which goes to the risk analysis that has to take place while we're working on this, right? So the risk is that when we're talking about wells, we're talking about millions of dollars, right? We're talking about, this is a humongous investment a company is about to take in, and you can say it's an investment, right? Because the reward is relatively high. If you drill into a producing reservoir, you're going to make a lot of money, right? So, but you don't always know. If you've ever seen a movie like There Will Be Blood, it's like a movie about early 1900s in the U.S. about oil and gas, about this oil and gas entrepreneur, right? they kind of just drilled in they had some geological concepts, right? Early 1900s, there's not much technology, but lots of dry wells, you can say. They're called dry wells, but were happening in that time because you would miss a lot, or you think you'd miss, and then you're actually like a few thousand or 100 feet from a reservoir, or you think you struck gold and you just struck a small oil reservoir, right? And we saw in like, I don't know if you're familiar with, but back in the day in the black and white movies, they would always show us someone who made it, who drilled for oil, and the oil is just gushing out of the rig, right? And it would gush out, and that meant like, oh, he made it. But in reality, that's not the case. That's actually really bad. That's a lot of money lost. No company now would want any oil to gush out or anything. We want to produce and optimize, right? That oil coming out and use it and sell it basically. So, but these are kind of cool sub facts, but whatever. But essentially, when we're talking about in producing or drilling into a well, we're talking about risk. At this point in time, the risk is extremely high, right? So we want to be able to define that risk. And the reason we can define that risk is it helps us understand the opportunity of success. So the risk is categorized across 4 pillars. So is there a trap, right? Is there something trapping the hydrocarbons? Like we've said, hydrocarbons do not, if they're not trapped, we can't really produce them because they just keep rising, right? And what is the source rock like? So that goes about to the rock properties, right? Is this a high porosity? Is there a lot of connectivity? Is this organic rich? Can it actually generate oil and gas? You know, like generally sandstone has a really high porosity, right? Of like 22 to 27 or something. That's relatively high, whereas shale has very low porosity. Uh, is there a cap rock, right? Is there a seal? Is there something preventing the hydrocarbons from escaping, and can we get to it, right? So shale is actually a really cool and interesting rock because it was a game changer or a critical point in the hydraulic fracturing evolution of technology, and we'll talk about that when we get to production or completions and talk about hydraulic fracturing. But shale is basically this rock that's almost a solid. It's like a solid. It's very hard to push anything through it, right? And the reservoir, which is the 4th pillar, is there a high permeability? Is there a high porosity to transmit all the fluids given the good conditions? So if we can combine or define all these 4 different pillars of risk or different chances of success, is that you can call it the overall change of success, which is the COS. But basically, we want to reduce uncertainty and we want to avoid dry wells, right? We want to make money and drill into permeable and porous rock structures. So, moving on to the exploration well planning, which is kind of the final stage of the exploration world or the exploration subcategory in the life cycle of a well, and we're basically deciding what's the first well going to look like. And the objective of this well is to, first of all, confirm that we can actually make money. We can drill and produce hydrocarbons. Sometimes you want to be able to collect core samples because, like we said, core samples will tell us about the porosity and properties of the rock. We can test the pressure, so through pressure transient testing, and we can take some fluid samples. So this is our first time where we're actually getting real live data that we can use and know what's going to happen with respect to the life cycle of the reservoir. And this is the first or the beginning journey of the well, right? We're going to, so we've defined the objective and now we need to define its location. The optimal location, usually you're picking more than one well, so when you're in the exploration phase, you'll do 1 or 2 wells or a few wells, right, depending on the size of the project. And you also want to know how you're going to build this well, so how I'm going to design my casing, What drilling programs am I going to follow uh, based on the pressures and the formation strength and the risk? So when we're going to go through what a drilling program is, that's the next category. But when we go through this well, is that when we find out the drilling programs, it will also tell us a lot about how well we can log, how well we can do formation testing to evaluate the reservoir in real time. And it will also sort of prepare us for the unknowns or the first set of unknowns. So unexpected pressures or lost circulations or changes in structural depths, right? So we want to kind of remove lots of the unknowns with our first few wells, because this will tell us more about how the next 60 years are going to be. Again, you have to realize that you're starting a project that you're hoping will be for more than half a century. So you're kind of placing your bets with a lot of uncertainty, but you want to be as accurate as possible, right? Okay. So let's move on to drilling. We're going to be talking about the rig selection, the well design, the casing program, the drilling fluids, directional drilling, which is kind of just like subcategory of drilling, but is the more relevant and it's the more common form of drilling now, and blowout preventers and safety. So another thing to note here, right, is that before any well is drilled in this previous category, we didn't talk about this, but in almost every oil company or upstream company or midstream company or downstream company, the number one priority is safety. And the oil and gas industry historically has kind of a bad reputation when it comes with this, but it is only due to the nature of the oil and gas industry. So due to the competition, right, between these companies, you're talking millions of dollars for a single given project or for a single given well or so forth, right? So because the stakes are so high, the advancements in technology and stuff like that is not discussed up until certain points of time. So it's kind of behaves like this private, very secretive world, right? Some of the biggest companies are oil and gas companies, and most people won't even know them by name. And that's the nature of the oil and gas industry, right? There's all these technologies, cutting edge technologies, innovations, creativity that take place, but no one will know about it. So the successes of the oil and gas industry are kind of secret due to their nature, but obviously the failures are not. So the failures are always advertised, right, due to the fact that their nature, but they are relatively uncommon. So the biggest failure I can think of, and we'll refer back to this more than once, is Macondo. So Macondo is a reservoir in the oil and gas, in the Gulf of Mexico, right? And I believe the operator at that time was BP, and basically the blowout preventer was not correctly implemented or cannot, whatever. There was an issue with the blowout preventer, and basically this huge oil spill happened, right, which impacted the environment, impacted the politics, impacted a lot of things, impacted the oil and gas market. Because when we're talking about oil and gas, you cannot talk about oil and gas without talking about the economics. And since it's a huge economic category in most countries that do produce oil and gas, politics are associated with it, right? So that's just the nature of the oil and gas industry. It's very politically driven. Obviously, historically, wars have been fought over energy. You don't have to go that far back in time to see examples of that. But there are lots of dangerous or risky things at play here, and there's lots of external things at play that are affecting these scientific decisions. So that's also something to keep in mind. But when we're talking about from the perspective of an operating company or an oil service company, safety is a number one concern. It is it's probably the most important parameter, right, like that every company has to be cautious of and ensure that they're doing it correctly, right? So in drilling is a kind of one of those high stakes, high reward fields, as a drilling engineer, you get to live a pretty cool life. You get to work with crazy technology, right? We'll go about what these drill bits are and stuff like that. But drilling engineers are kind of engineers that have to make correct decisions very rapidly as directional drillers. So you will see that in the next few slides. But when it comes to the drilling aspect to the life cycle of the well, is that you have to choose the right rig for the job, right? So depending on the depth that you're working with, you also want to know which rig you're going to work with. So depending on the water depth, well depth, location, and cost. So again, here now we sort of brought in that parameter we've been discussing about, which is cost. So just think money, right? Cost, revenue, whatever. But there's this dollar sign attached to almost everything we do now with respect to the life cycle of the well. So there are land rigs for onshore, so you can drill. For example, you've seen pictures of them, like the most common picture when you Google like a land rig. But you have to drill. Not all lands is the same, right? There is desert, there are swamps, like in Louisiana. Lots of the land rigs are on these swampy fields, or is in the like tropical jungles of Indonesia, or the deserts of the Middle East. There are lots of different environments, and these environments play a hand, right? These impact the rig structure and the rig installation on land. And then you have jackups for shallow offshore. And when we say shallow offshore, honestly, we're just kind of saying shallow because it's relative to the semi-submersible rigs or the drill ships, because that's for very deep waters, right? So Macondo was an example of a deep water, I believe. But yeah, so depending on where you are or where you think your reservoir is or where you're going to drill your first well, the environment has a humongous impact, and the depth of the well also has an impact. So when you think about, for example, in the 50s, in the Permian, the wells that were drilled were like 4,000 to 8,000 feet. And then in the Caspian Sea, they drilled the 40,000 feet. So obviously, those are two different drilling programs. Those are very, very different in nature in almost every aspect, right? So once you've selected your correct which rig or which depth or whatever, you need to also take into consideration things like the hook load, the pumping capacity, and the BOP compatibility, right? So when we're talking about this, basically at this point in time, we are talking about depth and we are talking about pressure. So just think of that. And these are the different factors. So the type of terrain, like I said, is it sand or is it swamp? The mobilization cost, weather conditions, and local regulations, right? And local regulations is kind of a weird one if you think about it, but it is very true because when you're in a different country, so for example, let's take a hypothetical company like BP is from the UK. If it's going to drill in if it's going to drill around Scotland, right? That's its territory. It's going to be very different than when it drills in the US or when it drills in, in maybe, I don't know if they have Russia, but let's say, for example, in Saudi Arabia or in Nigeria. All of these here now, this is where politics come into play. This is where, because the politics implement the policies, right? For example, in the US, New York State bans fracking. So you cannot frack in the state of New York, right? Whereas in Texas, you can frack. So the laws is that BP can't go to New York and be like, I'm going to frack and drill for blah, 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 hypothetically, right? You must abide by the rules. And now if you think about it in an interesting sense, is that these big companies that invest a lot of millions of dollars into research, universities, obviously they have a say in politics because they potentially bring lots of money to the country when it comes to the oil and gas. So now this they've become in a way like these political drives, right? And if there's wars being fought on this, so there each country has its own policy, each country has its own rules, and everyone must play by those countries' rules. So that is something to note, is that when we're talking about uh, the life cycle of a well, there's these two external parameters now that we must take into consideration that before we didn't, right? It's not just a scientific decision. It's not just a mathematically optimal decision. There's also a dollar sign parameter I have to apply to it and a political parameter that I have to apply to it. And when I say political, I'm just talking about the policies and the regulations of the country you're trying to drill in. Okay. So once I've had my rig, and I get generally the rig platform, it comes from an external company, by the way, and they kind of can move rigs around, uh, or the platform, right? So I need to design my well. So these engineers are going to design the structure of the well. So first of all, we need to know that when we're drilling a well, we do not drill it all at once, for obvious reasons. But so first obvious reason I guess that we should think about is you're taking this drill bit, right? And if you have never seen a drill bit, again, you can look for it. But essentially, it's this really twisted helical looking thing with diamond bits attached to the drill bit. And the reason they use diamond, obviously, diamond is the strongest rock in the world. So if I have diamond on my side, I'm probably going to break whatever rock is in front of me. And that's the logic behind that. And these drill bits, right? First of all, you're going to be rotating it. They rotate and they spin really, really fast as they go forward or down into the ground. So when I'm drilling, naturally, this high level of spinning, this very high rotation or high torque, and this pressure I'm applying and this depth that I'm going, what they call rate of penetration, it gets very hot, right? So when it gets very hot, the mud around it is going around and it kind of loosens up, and you have to circulate that mud out. So in the most simplest of terms that you can think of is if you were at the beach, and you had this toy shovel, and if you just stick the shovel inside the sand and twirl it around, you can go deep, but at some point you're going to get stuck, right? Whereas if you remove the sand with the shovel and then dip it, and then remove and then dip it, and you incrementally do this, you will go a lot deeper, right? So it's the same thing when you're drilling for a well. You need to drill incrementally. First of all, these drill bits, they get really hot and they get damaged, believe it or not, after all this usage. And you don't want to get stuck down there. So what you want to do is that you want to be incrementally drilling, stopping, cleaning. It's this circular process, this iterative process, and then you're choosing the direction, you're choosing all these different things. So when we say drilling, we're talking about rate of penetration, we're talking about horsepower, we're talking about torque, but we need to consider cleaning, we need to consider not to get any kicks. So all of these things are in play, right? And what you want to do is that so due to that is that when you drill a bit, basically you'll drill in a section and then you drill and then you seal it by a casing string. And then what these casing programs are is that you're trying to protect yourself or protect your well, your future well, from formation collapse or fluid influx or lost circulation, right? And high pressure zone. You basically want to avoid anything unsafe. And what you're trying to do is you build, and the way you build it is that you kind of drill a little bit, and that will be your widest part of your well. And of your annulus, you can say. And as you incrementally go down, you'll kind of get more and more and more narrow, right? And so that's also why you're doing these sections. And now chemistry comes into play, because what type of cement you put down there is highly dependent on the nature of the reservoir and how deep you're going to go. And there's a whole different levels of grades of chemistry that you can or different grades of cement that you must analyze as a chemist, or chemists will do this to tell us, okay, this cement is good for this section, then you need to use this cement, and then you need to use this cement, or whatever, right? They have to give you this proposal. And basically, the goal of this well design is to maintain the well integrity from spud to production. And what does that mean? Is that when we say well integrity, is we're saying, it's kind of like saying data integrity or whatever. It's just we're trying to say the stability of that well. To from spud to production, we want the stability of this well for its entire life, actually, to not, the cement to not crack, or the well to not have break points, or for it to lose the objective of that well. So if you're producing from that well or injecting from that well, is that we want this well to perform as optimally as possible for its entire lifetime. Okay, so now moving on to a drilling fluids. So a drilling engineer and a drilling fluids engineer and a managed pressure drilling engineer, MPD engineers. These are all different types of drilling people, right? And they focus on different things. But the drilling fluids, you can say, is the blood of the wellbore, right? Right. We have to, first of all, is that you're drilling, your depth is changing, right? And we already know that hydrostatic pressure, you should be familiar with it, but we want to maintain that pressure. So hydrostatic pressure is like the capillary pressure, basically, but it's with respect to depth. And so when we say hydrostatic pressure, it's with respect to some sort of fluid. So we're calculating the pressure with density and a change in depth, right? Which is very relevant or convenient for us here. But we want to maintain that pressure as we continue to drill, and as more fluid or as more like the mud occurs or whatever. So we need to circulate, basically, like I said, the same way we clean, we must circulate with fluids around the well, basically, to maintain this pressure. So we're kind of manipulating through the use of fluids, manipulating the environment of the drilling to maintain a hydrostatic pressure to where nothing like a kick or a blowout occurs, right? So the way we do this, like I said, is that hydrostatic pressure is the pressure with respect to density. So we want to monitor the density, the viscosity, so the pH is the acidity or the alkalinity or the salinity of our environment, right? And the whole point of this is to have a continuous, successful drilling operation. So it's the circulation of the fluid, and that's why they call it the blood of the wellbore. And you can basically include your own mud, and that's what they do when they're circulating fluid. They're including their own mud to manipulate that pressure. So you have water-based muds and oil-based muds, right? And this drilling fluid usually is defined as a managed pressure drilling engineer, and they're sort of in charge of the drilling fluid while the drilling engineer is drilling, right? Which brings us to our directional driller. So so starting from as a drilling engineer, right? Historically, only vertical wells were drilled. When you talk about the early 1900s up until the 60s or something, or the 50s, vertical wells were drilled, and as the technology advanced, we could sort of drill further and further down, right? But if you think about it, that's not necessarily that optimal, given that we have a reservoir. Potentially we can drill one well to cross or stay inside the reservoir, so go horizontal wells. So that technology evolved, and then we were able to drill horizontal wells. So you can think of these very big L-shaped wells, is that you'd go down to the reservoir, and then you put the horizontal side throughout the entire reservoir, and you perforate there, and it allows you to produce a lot more oil. And if that's confusing, the way you can think of it is that when you're drilling a well, not the entire well is not touching the reservoir side, right? So you're going to perforate only in the exposure to the reservoir, and then naturally the oil will come out. Sorry. But when you increase, so the more you increase that surface area of the uh, those perforations, the more oil you can produce. So what L-shaped wells or horizontal wells allowed is that you can increase that surface area by a drastic amount for your wells, and you perforate because you're exposed to more of the reservoir, right? But then as technology advanced more and the drilling engineers advanced more, is that they became so advanced that they can kind of direct the well at will. And you have multiple different shapes now, the S shape, the J shape, multilateral wells, and so forth. But the essence of it is that with the technology that drilling is, and this is why I said earlier that a directional driller or a drilling engineer is sort of making really high risk, high reward, or very high risk decisions relatively fast, is that they're drilling live. You know, they're drilling live and they're deciding where to go. And now that they have this ability, which are defined in these three categories here, is that this build, hold, drop, right? So you can build, is that you're building is kind of like turning, and you can choose the angle, the azimuth, and so forth, and you can hold that there, then you can drop a bit, and you can hold it there, and you can drop a bit. So you can essentially, in the 2D world, draw any well shape that you like. And then it also opened that door for, okay, well, if I have one well at the surface for economic reasons, for environmentalist reasons, you want to be as clean as possible environmentally, is that now I can drill one well from the surface, and then I make like a spider or multiple outlets of different wells on the bottom, right? So now with this technology advance is that you can build these multilateral wells and extended reach wells, which are basically spiders kind of, or they look like caterpillars under the ground. And the objective is to increase that surface area, to increase production, and to maximize your return and maximize your exposure to the reservoir, right? So once this was enabled, this drilling became very interesting, and now we've reached the point where our drilling engineers can sit at an office and decide remotely how to drill, right? With these tools. So lots of these technologies are still advancing, and they're nowhere near where the oil and gas industry wants them to be, in the sense that there's so much room for improvement, right? And you can also think about the artificial intelligence aspects, the algorithmic aspects of optimizing the decision on the direction. Can you automate some of it? There are lots of really cool topics that you can get into here with directional drilling, right? And I have this point here about MWD tools and LWD. We'll talk about those with when we talk about logging, because they kind of go into the logging world. But I bring them here because it's the drilling engineer who will kind of gather that information. And these are two also very innovative and interesting technologies that came after the logging world. And basically, it's while you're drilling, you can gather some information, and you can also do one or two logs while you're drilling to get some information about your reservoir, and that can actually help you decide where to drill next or which direction you should move to, right? So if I drill a certain part, log it, and then that will tell me where should I drill next, right? Should I steer to the left? Should I build? Should I hold? Should I drop? And so forth. And before, you couldn't do that. Before, historically, up until recently, like when I say recently, I'm talking about like 20, 30 years or 40 years, but you couldn't, you could just drill, and then you would run your logs through a wire line, and then you'd make some decisions and try to improve your decisions as you go. So this was a huge breakthrough. Culturally, when it came, people always say, things will replace everyone. We're seeing that now with artificial intelligence. AI will replace software engineers, and then it doesn't. RPA will replace all these people, and then it doesn't. And in reality, it just changes the nature of your job, right? Well, when MWD and LWD tools came, everyone said that it will replace wireline, right? You will no longer need wireline. You just do it on the drill job. But after a few decades, what people are realizing is that you can do both, and both are beneficial. For different types of analysis and different types of data acquisition, right? So that's something to note. That also in this industry, you'll see that people kind of take a really long time to adapt to a technology. And once they adapt, they generally have this like understanding that it will replace a lot of things. But in reality, it's just an additional layer of data and additional layer of innovation that can help us make better decisions. So, and there is a huge amount of room for improvement and innovation in the industry for these kind of things, right? So R&D is a field of its own. So when I talk about these things, they're like in wireline R&D, in directional drilling R&D, in fluids R&D, in the cementing R&D, coil tubing R&D. You know, these all have their own world. And if you think about it in terms of an industry, we're a lot older than technology, but in terms of the advancements of oil technology with respect to other industries, we're pretty new, right? Like in the early 1900s, the way they would drill was they would send someone with nitroglycerin and just blow up. It's equivalent to TNT and just kind of like blow it. You have a huge explosion and then continue to do that, right? So the world has changed in a little over 100 years, and it's been changing quite rapidly in the oil and gas industry. And finally, in the drilling world is that we will talk about blowout preventers. So the blowout preventer, the BOP, is what caused the Macondo or the Deepwater Horizon or the BP oil spill, whatever you want to call it. But it was a huge lesson learned for the entire oil industry and for the people involved, right? But it's basically your most important part against any uncontrolled flow, basically it blocks anything from coming back out that you don't want to come out. So they are massive valve systems, and they're installed on the wellhead to contain unexpected formation pressure. And actually that brings me to a topic that the surface of a rig has its own tools, and like the Christmas tree, the valves, and the pressure head, and all these things that require its own expertise. There are different companies that work on it, you know, and so that's also sort of a separate field that you can get into. But the blowout preventers, they're these big valves systems, and they have these annular preventers and ram preventers, and they can seal around the pipe, and they can seal open holes or cut the drill pipe if needed. And just so we're familiar with these topics or these terms, you know, when you're considered an open hole is when you haven't done the casing yet. So you haven't, there's cased hole and open hole. Those are the two categories. So obviously you start out with open hole and then you move to a cased hole. So in all three scenarios, or I guess the two main scenarios, the blowout preventer can be your lifeline of safety. And they have like this kick detection procedures, and they well control training. And this your first line of or it's your main line of defense when it comes to drilling safety and even production, right? So like it's environmentally protective. It has to follow, again, here we're talking about the location or relative to the location, but it's the regulation and compliance. There are like in relative international standards, but then you have to be aware of the country standards as well when you're talking about which blowout preventer to use and so forth. And the goal of the blowout preventer is safety. It is the safety of the rig, safety of the people, safety of the environment. It is just safety. It's to secure. It's there as like a lifeline or your life vest on an airplane, your life jacket, I mean. It is your last line of defense, right? So these are all the different topics we've talked about with drilling. So we talked about fluid engineers, drilling engineers, chemists, and even surface engineers. So now we can move on to logging. So in our well world, in our well journey, right, is that we've done our geological model, we've identified the spot we're going to be drilled in, and the drilling engineer has finally drilled the well, right? And now the well exists. So now the next step is to get the information about the reservoir and the rock, and the way we do this is with logging tools. So wireline logging is, I guess you can say, the golden standard when it comes to logging or when it comes to data acquisition or reservoir characterization. And then LWD and MWD we've talked about. And then the porosity permeability indicators, basically the different types of tools to acquire these parameters, so porosity and permeability. And then we'll talk about saturation, which is, like we mentioned, it's this relative percentage of water, oil, and gas. And we'll talk about Archie's equation. Archie's equation is one of the most important equations in petrophysics, one of the most important equations in the logging world, and we'll give some history back on that. And then finally, in our well journey or our life cycle of a well, we're going to be identifying our producing zones or our productive zones, right? So, wireline logging is basically downhole measurements after drilling. And why is it called wireline logging? Is because you're sending this tool and you're lowering it on this electric cable. So it's like this actual wire. And this big wireline truck, and this basically has this humongous wire tied to it. And you will attach the tool. A wireline engineer will do this, will attach whatever tool they're going to run. And they attach it and they'll drop it down hole. They run it down. Sometimes you're measuring as you go down, sometimes it's down and up, and sometimes you put it on down and measure as you go up, right? Depending on the tool. But here is where it gets pretty interesting in the world of physics. Like I mentioned, we use Einstein, we use Archimedes, we use a lot of crazy nuclear technology, we use a lot of different cool things, and this is kind of where it comes to play, right? So, for example, here we're measuring gamma rays, resistivity, density, the neutron response, right? Because when we think of neutron, well, that's similar in size to a hydrogen, right? Because hydrogen only has one valence electron, so yeah. So also we measure through sonic, and the objective of a wireline engineer is to provide formation data, high resolution formation data, and being able to identify the properties that we discussed earlier on in the lecture. So things like the lithology, the porosity, and the fluid type. And remember, we can kind of relate those to permeability and so forth. And this, in the world of the painting that we've been creating an analogy to, this is kind of where we're drawing our picture more defined. Our painting is becoming more and more defined, right? And we're going to, hopefully at the end of this different tools, is have a really good idea on what our reservoir looks like. And when I say that, I mean what our formation rock looks like, what our fluids look like, what our saturation level looks like. So we kind of are supposed to understand by the end of this what everything looks like, okay? So wireline logging is kind of really cool, and like I mentioned, you can run lots of different tools. Moving on, sorry. Okay, so LWD and MWD is, like I said earlier, is that it's your real-time logging while drilling, and you are either measurement while drilling, which tells you, you know, the inclination, the azimuth, and the mechanics, so sort of like the drilling characteristics, and helps you know where to drill to next, and is giving you that data. And then there's the LWD, which is logging while drilling. And generally, you run a gamma ray or resistivity log, and those are your two initial logs that you generally run on almost every well while drilling. So doing it while drilling or doing it with the wireline are both important. They're sort of the first type of indicators if you have hydrocarbons, right? They're hydrocarbon indicators. And the reason you do LWD and MWD is first is that you can understand your reservoir more, but generally that information is kind of guiding your drilling. So you're using it to guide your drilling. And the point of doing it while drilling, why is, again, the objective is to reduce the risk, maximize production. So when I reduce the risk of messing up on my wireline or not knowing which tools to run with wireline or getting stuck in pipe or whatever, is that I'm essentially taking that risk away while I'm running a log while drilling, right? And this helps me with my well placement and my reservoir contact, or that reservoir exposure, like we said, to know how we can maximize that surface area for downhole information. So moving on to the tools, this is kind of the wireline world, but these are the tools that they run. And we are essentially trying to get information about our porosity and permeability, right? Because porosity and permeability are the two things that we need to produce oil. They're the two main things we need. So under the porosity logs, we have the density log, the neutron log, and the sonic log. The density log, obviously, the lower the density, the higher porosity, and the neutron log is sensitive to hydrogen, and that's due to the size of the hydrogen atom. And that kind of tells us, right, because what has hydrogen? Well, water and hydrocarbons do. So it tells us the big picture, not necessarily what's oil or not, but it will tell us ideally if we have a good amount of hydrogen, we generally will have a good amount. If we've done our part or done our homework on the other aspects in the previous life cycle journey steps, is that we will have a good amount of hydrocarbons, right? The sonic log, again, we're kind of similar to the surveys in the sense that we're sending a pulse out and measuring its return. But these sonic logs, they measure the sound travel through times. If it's slower, it's more porous because it's gone through a longer trajectory, right? If it just hits rock and comes back at you, obviously it's not porous. So the sonic log tells us, so the sonic, neutron, and density log are probably the three most important logs that tell me about my porosity, right? Now my permeability indicators is that I have the resistivity and porosity, where basically clean sands with a good porosity often have higher permeability. Again, we said earlier on that that's not an absolute, but it is something that we do see in nature, is that the better porosity, generally the better permeability, right? NMR logs are nuclear magnetic radiation log tools, and they provide direct permeability estimates. And the production logs, the PLT, they show actual fluid movement in the well. So these are basically just different logs that will tell me. And by the way, just to note, these are run at different times throughout the life cycle of the well, right? It's not like you run one log after the other. You generally, but you might run one job and then you go back and do something, then you run another job or so forth, or drill more or whatever. So it is this iterative part, and there is overlap. But these are the different logs that you'll run. Basically, your goal is to identify the best places or potential or most probable zones that will have hydrocarbons, not just having hydrocarbons, but hydrocarbons that you can produce, right? Hydrocarbons that we can take out of the ground successfully and economically. Okay, now moving on to saturation. If you're not familiar with Archie's equation, Archie was a physicist in Shell, I believe, and what he was able to discover in this really important paper, you can read it till now, it's not that long, so I recommend you guys read it, but he was able to discover this relationship between saturation and resistivity, and that kind of should click in your head is why we measure resistivity and what are resistivity logs for. And if I can measure the saturation or resistivity, I also will know, or I have porosity, right? So in the equation that's relating rock resistivity to water saturation is that you have A times RW, right, divided by porosity raised to the M multiplied by RT, all raised to 1 over N, right? Where A, M, and N are empirical constants. We can get into that in a second. Porosity is phi. RW is the water resistivity, and RT is a true formation resistivity. So when Archie was writing this paper, or his discoveries, they were made on sandstone, and they were empirically derived. This equation was empirically derived. And what that means is, if you're not familiar with that term, is it was not derived through theory or proof, but it was defined through observation. And one thing that's unfortunate for that is the observation was done on very ideal terms with a really high porosity sandstone, and they found that these constants work well, which they don't really work in other environments or other formation rocks or different porosities. But what people were able to use in the oil and gas industry, and what lots of tools will use, and usually they have this equation in almost every logging tool, is that there are different modifications where you can use it to apply it to the rock formation you have. And that's why this became a very important equation. So also something to notice in physics, and it's true in petroleum engineering or petrophysics, is that when someone can explain something in a very simple equation or in simple terms, and you can take that explanation and sort of extrapolate it to lots of different categories or different scenarios or situations, it becomes very highly important. You know, like Newton's laws are useful or are considered very important because they don't really fail unless you're next to a black hole. And these three laws, they were not even written mathematically. They were sort of just written, right? That's what makes it beautiful. In physics, when we have something we can explain in simple terms, it becomes relatively important. And that's Archie's equation is definitely one of those equations in the oil and gas industry, because you're able to relate resistivity to saturation. And if I can relate that, my resistivity tools, I can easily measure resistivity, but it's hard to measure volume. It's hard to measure saturation, right? So that's a really important or interesting topic to note, right? Like we talked about Archimedes' principle. Archimedes, he was able to do something so simple as to relate the displacement of volume to density and proportionally analyze and solve for density. And that's what makes it so important, right? So this is why this is one of the most important equations in the oil and gas industry. It might not be used or it's not applicable to lots of things now, especially when we talk about reservoirs. There is conventional and unconventional, and that's also another arbitrary term. Conventional oils are basically things that we've been successfully doing for a few decades, and unconventional is something new to us, right? And we'll get into different examples of those when we get into the production engineering. But this is the Archie's equation, and we use this. If you are thinking of the logging tools, you should be able to see the importance of this equation. Because if I know water saturation, that will tell me about the oil saturation as well, right? And essentially, I want oil. So, this brings us to the final journey of the wireline world, where we've acquired all this data, we've detailed our painting, we have all the information, and now we know where we should perforate the well. So perforate is just to put holes in terms of if you've never seen it. And what they do is that you have a well, right? So when we're talking a well, we're talking a cylinder. And they perforate in a helical pattern to optimize the surface area. And it's just this gun that will literally kind of like a huge, really powerful gun that will shoot through your metal well and into the reservoir rock, allowing the drainage to start, right? For allowing your oil to be produced. So we combine all the logs to finally know whether we have our clean sands, do we have our good porosity, do we have the high resistivity, do we have the low water saturation, do we have the positive permeability indicators, and to integrate all the data we've acquired to tell us with the production history, and we want to basically select the best place or the best collection of places to maximize our production. So what this means is inherently is that you're acquiring all the data and you're finally drawing a conclusion on where you should perforate and where you should start producing from your well. So again, every single stage is just as important, right? There's no stage that is more important than the other. If one of these stages fail, your well is not going to be economic, and it's that simple. So the wireline engineer has gathered all the information, and now it's time to perforate the well and to start completions. And completions is multiple stages. So we're going to talk about each stage as they come, but we're going to talk about the wellbore preparation, the perforations, and also perforations like the drilling people do perforations, wireline do perforations, and completion engineers do perforations. So essentially perforation is putting a hole inside your well to achieve something. Then there's packers, tubing, the hydraulic fracturing, and stimulation and artificial lift. And these are different aspects. So when we combine it all in completions is because we're completing the well, or we're running a production well, right? We're running a producing well. But all of these come at different times. And all of these, or some of these, there are frac engineers, right? There are acidization chemists and acidization engineers. There are artificial lift engineers. And even within artificial lift, you have different categories as well. So just in the back of your mind, you should realize that there's so many different fields within petroleum engineering that you can get into, specialize in, and learn about, right? So when it comes to the wellbore preparation, after drilling, you need to the well is finally cleaned out. Like I mentioned, this is incrementally cleaned out. Hole cleaning is something that's done throughout each interval of drilling. But in this final phase is that you clean out, remove the cuttings and debris, right? This is what hole cleaning is. The casing is cemented, and we do this to ensure zonal integrity, and basically, again, that's just our well integrity. And the wellbore conditions are evaluated before running tools, right? So this part is done in completions before you're running your logs, right? So after drilling, before logs, right? And here they do take care of, or they do check the cement quality and the casing geometry. And when it comes to perforation, like I said, it can happen in different stages, but you're creating the flow paths essentially from the reservoir into the well. These are massive guns, by the way, but basically these humongous guns shoot shaped charges through casing and cement into the reservoir. So it has to go through quite a bit. And you're basically creating these tunnels that allow the oil and gas to enter the wellbore and for drainage to start. When I say drainage, it's coming from the reservoir into the pipe, right? Kind of like stabbing a balloon with a straw. Naturally a water balloon with a straw, and naturally water will start to come out through the straw. And the perforation strategy is based on the shot density, the penetration depth, the phasing, and cluster spacing. But this is basically knowing how your perforation should take place, and also the patterns that I talked about. And it must be timed with the reservoir pressure, the fluid type, and completion design. So all these parameters are being taken into consideration. And the reason you're doing that is you want to maximize your flow, and you want to minimize formation damage. And the reason we want to minimize that damage is because we want to control the pressure change and the integrity of the well and the integrity of the reservoir through that entire time period. So in completions, there's also packers and tubing, and that's controlling the flow and isolating zones. So tubing is the production conduit through which fluids flow to the surface. So that's when you're actually controlling the flow. And packers are these seals. You can think of them as like these. You're basically blocking that area from your wellbore from the flow. And you do this in sections, and you can do this for different reasons. But it's basically zonal as isolation, which is going towards, again, for optimizing production. So you can do selective production, or if you're going to do some sort of injection, you want to be able to control this, right? And you want to prevent any cross flow between formations and protects the casing from corrosion and high flow rates. So again, this goes back to that you want to manage and safely channel the reservoir fluids to the surface while maintaining the pressure control. So all of it is about the pressure, right? Hydraulic fracturing. So here you're increasing the reservoir contact and flow capacity. What that means is, so let's talk about what hydraulic fracturing is before we go through these points. But hydraulic fracturing is that you take these like 200-ton trucks, right? And you should see a picture of it, but these 200-ton trucks are all pointing to the same thing, and you shove or you push at a very high pressure this amount of fluid. And usually in a frac job, you have this thing called padding, you have this fluid, and you have some sort of proppant, right? But essentially what you're trying to do is you're trying to increase the permeability. And how you're doing that is that you're pushing this water so fast and so strong into the producing zone that it will kind of like crush and open the producing zone by a bit, right? Because you kind of pushed all of this so hard that it kind of breaks the rocks, opens them up, and then the proppants will kind of keep it open, and that allows for these for higher production of oil for that given time, right? So what the objective of hydraulic fracturing is that you want to increase your permeability by more than one. So you want to maximum double it, triple it, whatever it is, but you want to increase your permeability by a rate more than one. So 1.2, 1.3, 2, whatever you want to do. And fracturing is, again, is shoving all these barrels of fluids. And in the 70s, when this became more popular, they were doing maybe like 100,000 barrels, and that was considered a lot of fluid of being fracking job. And it was considered almost insane to say that, oh, we'll reach like 1 million barrels or whatever. But then the frac boom happened, right? And the frac boom happened in the 2000s, and what that was is that they were able to frac shale, and they had the technology to frac these really low permeable rocks where they knew there were reserves, right? So again, reserves are, we know the oil is there, but it doesn't become a booked reserve, or what you can say a booked reserve, unless it's producible, right? So just because you know oil exists somewhere does not necessarily mean you can get that oil out. And there was a lot of rocks, or a lot of formation rocks with reservoirs that had such a low permeability that we did not have the technology to produce that oil, right? And that's another thing to keep in mind, is that there is a lot of oil under the ground that doesn't qualify as producible. And this was one of those times where you can see that a change in technology or an innovation completely changed the entire oil economy and market. And that was in the early 2000s, I believe you could say 2004 or something, and it was just a huge boom. But then obviously that led to an oil economic crash, and that's for a different topic, but it was due to this hydraulic fracturing technology that came into play, where we were able to frac at a much higher amount of fluid and frac very low permeable rocks, and then make it not just frac at that, and also make it economic to produce the oil from those formations, right? So that's what hydraulic fracturing is that you shove this padding down, and then you push fluid, and then you push proppant. And the idea is that you want to increase the permeability of that rock. So again, you're kind of stimulating permeability, and these proppants are placed in the fractures to keep them open. These proppants for oil and gas, they're very small. They look like small marbles, like your marble toys or something, but they're made of usually ceramic or sand. You can even push sand. They do that. Is that if I take a sand with a better permeability than my rock and I push it in there, I will have that be used as a propellant, right? And when I improve the permeability, I can enable an economic flow or an economic production of my reservoir. So that became the most dominant way of producing oil or stimulating, I guess you can say. But other forms of stimulation that we'll mention here, but they're not as common and they were more valuable back in the day when this technology didn't exist, was acidizing and matrix acidizing, where basically you use chemists to find ways that can manipulate your source rock or manipulate the permeability through adding these chemical fluids. Also, something to note about hydraulic fracturing and its technology is that if you've ever seen these proppants or the padding or the fluid that they put in, the fluid, you want it to open the formation rock or make that gap for as long as possible, right? So they have these fluids, and this is a lot of chemistry that comes into play, but they have these fluids where at the surface conditions, they behave like liquid. It's like water. But as you go to the very high temperature and high pressure of a reservoir, it becomes almost gooey like jello, right? And it becomes more sticky, and it can stick, and it can hold the holes up and increase that permeability for a longer period of time, right? Because when you're talking about you make a crack in the ground 6 to 10 or 20,000 feet underground, that crack is gonna close almost instantly after you do it. So you're trying to elongate that for as long as possible. And when you do that, they use these really interesting fluids where a fluid under one temperature pressure condition will behave one way, and in a transient pressure temperature condition, like falling through a well, will behave another way, and then in the frac job in the reservoir, it will behave another way. So if you think about it, that's pretty interesting, because in 3 different scenarios, that fluid has to behave differently and successfully behave that way for this frac job to succeed, right? So the amount of technology and the amount of research that has gone into that is quite abundant. And that is hydraulic fracturing. When we talk about the frac boom, it was in shale. So when we talk about shale, you can apply it obviously to carbonate reservoirs, low perm sands, but shale is basically, think of it as like this black rock that you could not pour water through it. It looks like solid, right? And so lots of oil that we know exists there, because we see shale, right, in a lot of our other conventional oil reservoirs. We know that that's an indicator. But we're not able to produce from then, and then all of a sudden we're able to produce. You can imagine the drastic change in the economics of oil and the technology, right? Because now that's opened up a new world for producing, and we can now move to the next stage, right? Because when we talk about production and engineering, we'll talk about the different phases of recovery and what that means. But you don't really recover all the oil that you know exists ever, right? And you want to maximize that as much as possible. But we'll talk about the percentages of what those are when in the more appropriate slide. So that's hydraulic fracturing and stimulation. But the goal is you want to maximize production rates. And now you can imagine when you have these horizontal wells and the extended reach wells, and you're just fracking across the multilateral wells and all these L-shaped wells, is that you're really improving the oil production by magnitudes, right? By order of magnitudes that you were not able to before. And last but not least is the artificial lift. So this is also another form of the strategy of what we're talking about, is that we want to improve the production of oil, but this comes in more of the final stages or in the secondary stages of recovery, right? Because when we first drill and we perforate and we're producing oil, we're relying on the massive pressure of the reservoir that's sort of pushing the fluid into our well, and we're just producing that based on the reservoir pressure. And that's sort of the first stage. But after that, you kind of have to decide what are you going to do to maintain that, right? So in the next phase, you kind of have other things, but pumps or artificial lift is in the second and tertiary phase where you're trying to optimize your oil production. And what you're working with is that you're using some sort of pump or lift to mimic the pressure change, right? So like I said earlier, fluid only moves with a delta pressure, so you're trying to stimulate that delta pressure to where you can economically still produce, right? So you want to stimulate the pressure or help the increase the delta pressure when your reservoir pressure has decreased and is no longer enough, right? So the different types of artificial lift here is you have the ESP pumps or the electric submersible pumps. They're very common and they're a high rate lift for deep wells, so you'll see them more in offshore and so forth. You have the rod pumps, or also known as beam pumps, and they're more common onshore and they're reliable for medium rates, so they're more common, I guess, for certain scenarios on land. You have the gas lift, which is you inject gas to lighten the fluid column, right? So you're kind of manipulating the fluid nature for it to rise more, or because you're reducing its density. You have the plunger lifts, so it's like a cyclic lift for low rate. But essentially, all of these is that you're using a pump or a lift to improve recovery and to extend the life cycle or the life journey of that well, right? You want to get your money's worth from that well, so you want to maintain and increase production as reservoir pressure decreases. And that is the purpose of the artificial lift. So, we're done with our completions. We've seen how completions are used throughout the different stages of the life cycle of the journey of the well, how it's used after drilling, before wireline, after wireline, after reservoir pressure is not enough, after stuff, so in all the phases. So completions is kind of something that's used up until abandonment or P&A. And when we say P&A is we're plugging and abandoning the well, and that's when we're kind of sealing off incrementally the well until we seal off the top to minimize environmental exposure or environmental problems, right? So we're kind of focusing on that safety again, focusing on that environment. And this is also a relatively new technology when you talk about plugging and abandonment. You know, it wasn't up until the 60s or 70s people just used to throw kind of like random things to close off a well, and there was no standards or regulations on it due to the fact that most countries lack the knowledge, and even most people lack the knowledge on what was impacting the environment, right? But as people became more environment aware, we gained the knowledge about that. The oil and gas industry also adapted by using the plugging and abandoning procedure, and that also has its own process, right? So that's completions. Completions goes through every slice or every step of the life cycle of a well. But now we're moving on to a more holistic and again collective concept. So when we're going to talk about production engineers, it's the same for reservoir engineers, but they're not working with just one well. They're making decisions on the collection of wells. So they're making decisions on the reservoir level, right? They're thinking of how to optimize. So if I have 30 wells, for example, hypothetically, is how can I optimize my production from this reservoir with the 30 wells in mind, not just one well, right? So we're stepping out of the well journey, and we're kind of looking at our entire reservoir, right? So, production engineer, what they're trying to do is they're trying to maximize all three recovery phases. So we have our primary phase, our secondary phase, and our tertiary phase. So when we say primary recovery is we're relying on the natural reservoir drive. So we're basically relying on the reservoir pressure to push the oil into our wells and for us to produce it. We're not really doing any of the work. We're relying on the drainage of the reservoir, right? And then in secondary recovery, this is where we're strategically making additions to our reservoir with either infill well drilling, water flooding, or gas injection to basically decide how to optimize that. And finally, tertiary recovery, or also known as EOR, and that stands for enhanced oil recovery. Uh, we have the CO2 injections and chemical enhanced oil recovery or thermal floods. We'll kind of define all of these in a few slides. And then also a production engineer. So the categories of which he's working with are all these three phases, and they really are, when we say production decline, right? Because over time, your production will naturally decline. And every time it declines, you kind of try and push it up again. And then you push it up again. And that's that secondary and tertiary recovery. So you're looking at decline curve analysis graphs or decline curve analysis data. You're looking at well performance monitoring. So that's like pressure transient testing, GOR, and the water cut. And you're looking at also or you're trying to forecast, right? So you're trying to take all the data that you're getting from production, so from how much oil you're producing per day or whatever, and all the data you got from the wireline guys and from the drilling guys and from the completion guys and the production logs and so forth, and you're trying to build different scenarios and forecast those scenarios and see which one is the most optimal. So you're kind of basically, you're the strategist. You work with the reservoir engineers, but you're the strategist that's trying to optimize this entire reservoir. And that's an economic thing. So your main constraint is being economic, which is so your dollar value, right? And the production enhancement methods that we'll talk about is like infill well drilling, water injections, gas, CO2 injections, artificial lift systems, and then workovers and well stimulations, right? So in production engineering, we can go through these. First of all, let's talk about percentages, right? So let's assume that the reservoir is 100% of oil, right? We have our reservoir set 100%, and our objective is to get as much as possible. When you think about primary, second, tertiary, most people think that, okay, I'll take some in primary, second, and tertiary. I take all of it in tertiary, in the secondary and tertiary recovery. And that's just not the case. The current technology, in the 20th century is that we're talking about primary recovery was like 10 to 12%. Secondary recovery took you to like 20, 24% if you were lucky, and tertiary recovery took you to 30 to 40%. And then with fracturing and the advancements of technology, you were reaching higher, like 50 or whatever percent. But in reality, you're not taking most of the oil that exists, that exists, simply for the fact that you're not able to. You don't have the technology to do so. And that becomes one of the reasons why petroleum engineering is so relevant and so still high in demand, is that there's so much oil that we know exists that we have not been able to technologically or economically produce, right? So just keep that in mind, that when we're talking primary recovery, we're talking 10 to 15%. When we're talking secondary recovery, we're talking 20 to 30%, right? Tertiary recovery, let's go crazy and say it's a big number. We're talking 30 to 50 to 60%. No, we haven't even gotten close to taking all the oil out of a reservoir, or even reaching the residual oil. Like if we were talking about this entire reservoir as a whole, we're not reaching those stages of immovable oil or immovable water, right? On a reservoir level. Obviously, these were with respect to capillary levels, but just to keep that in mind, right? So how does it work then? So we can take the Permian. The Permian is a really good example because it has a lot of wells. It has most of the U.S.'s production. So if you want to learn about history, it's always good to go back to these old reservoirs, right? And the ones that are more difficult, right? Like Saudi, produces oil so easily that it's not the same. But in the Permian, post-World War II, in the 50s and 60s, they drilled vertical wells, like I had mentioned. It wasn't about until the 60s and 70s that they started doing infill well drilling. And what that is that, let's say you have 5 wells, hypothetically. And I noticed after 10 years that if I drill a well between well 1 and well 2, I will improve my production. And if I drill a well between 4 and well 5, I can also improve my production, but not necessarily if I drill it between 2 and 3 or 3 and 4, right? So this is hypothetical. This is where infill well drilling becomes very good, is that you kind of understand how your reservoir is working after a certain amount of time. You can optimize how to improve that well, um, or improve that production by drilling in certain spot. And the reason they call it infill wells is that you're kind of like filling in the gaps, right? And then we have water injection wells. So this is where we take maybe a producing well, or we drill a new well, and we change it to a water injection well. And water is cheap, relatively. So what they do is that they take water from the surface or water from an aquifer, and they pump it into a well to stimulate the production of another well. So for example, let's say I have my 5 wells. It might be better for me, due to the fact or the nature of well 5 is to change well 4, which is not producing as much, into a water injection, and I will double or triple my production by injecting it and helping well 5 out, right? Rather than just drilling a new well or drilling an additional well. So water injection wells sometimes are existing wells that I convert from a producing well to an injecting well, or from or I drill a new well and I use it to inject water. And if you inject water at high speeds, you're not trying to frack or anything like that. It's not the same process or concept, but what you're trying to do is you're trying to help the flow of another well, right? So you're aiding or improving the production of a well from your injection, right? And it makes sense because you're manipulating pressure, you're manipulating flow, and so forth. Gas and CO2 injection is a lot more expensive, but it's trying to achieve the same thing. And then artificial lift systems is what we've talked about, is the ESP pumps, gas lift, and the rod pumps. And then we have the workovers and well stimulation, and that's the idea basically the fracking and acidization. So what a production engineer is doing is that he kind of joins the party early on, and he's monitoring it from the entire life cycle, or but here the life cycle of the reservoir, and based on the different forecasts with these different things at play, right? So for example, he could predict that the next 10 years they'll infill well drilling, and then the next 10 years they'll do water injection and infill well, and then after that they'll do artificial lift, and after that they'll frack, and then he sees on the 50-year span, or they see, sorry, on the 50-year span, what will that reservoir look like and what will my production look like. And then they will start another scenario, a different forecast, had they done a different sequence of events or different selections of improvements on production, and they will try to find the best route for this reservoir. And that's the goal of the production engineer, is to improve the production, maximize the production, and they are working on a holistic view on a reservoir level, not on the well level. Sorry. Finally, we are going to get into the reservoir engineer. This is one of the coolest fields in the oil and gas. Lots of people in university tend to want to become reservoir engineers. And I think it's just due to the analytical side, similar to production engineers, but they get to work with like lots of cool simulators and simulations and models and so forth. And there's an economic aspect to it. So let's get into it. The core responsibility of a reservoir engineer is to use the characterization and the data from that's acquired from that well to try and find the oil and gas volumes in place, also known as OOIP or OGIP. They want to evaluate the reservoir drive mechanisms. So that's the solution gas drive, the water drive, the gas expansion, etc. But basically, they're trying to understand all the natural drives that are pertaining to this reservoir, and they want to predict the production performance over time. So the production engineer will do all these different things, but the reservoir engineer is sort of looking on the best performance over time and try to predict that based on the different forecasts and modeling. And they want to recommend field development plans basically to the operator or to whoever's uh, oil that is or the project that is, because their plans or their simulations, they will tell the team basically which way to go, right? So they also assess the economic value of recovery methods and future investments. This is just something natural, again, like all the other topics, is that when we're talking about production, we have to do it within the constraint of economics, right? So, in the details of the reservoir engineer, or different topics that a reservoir engineer will look at, is the reservoir characterization and integration. So they take all the different multiple data sets to really understand the reservoir and to be able to use that understanding for predictability. So they take the geological data that we talked about, so structure, faults, and natural fractures, the layer thickness, and the heterogeneity. So also heterogeneity versus homogeneity. I don't. If you're not familiar with those terms, you can have like a heterogeneous mixture or heterogeneous permeability versus a homogeneous. So these hetero just means multiple different or different, and homo means the same. Homogeneity means the same. And then they use the petrophysical data, so the porosity, permeability, saturations, and capillary pressures, and that are derived from all the logs and the core analysis and the samples. And they take the fluid properties, so we talked about like the bullet point, solution GOR, oil compressibility, the phase behavior, the viscosity, and they use it to build realistic reservoir fluid models, right? And then they also have dynamic production data, right, from the production engineer throughout the years. They have the pressure transient testing, the pressure transient analysis, the production rates of the different fluids, the well test results, and the water cut and GOR changes over time. Sorry. So what they do with all this data is that they run multiple different reservoir simulations. And what a simulation is a numerical model that predicts how fluids flow through the reservoir over time. And they use this to forecast future production. They predict pressure depletion and where bypassed oil may remain. They test completion strategies, vertical versus horizontal or multi-stage fracs or hydraulic fracturing jobs. They compare secondary and tertiary recovery methods like water flooding, gas injections, CO2 injections. They optimize infill well placement, like I had mentioned earlier, and well spacing decisions, right? And the simulation models is that you have two main categories, you can say, of those models. You have the static models and dynamic models. Static models are more geological models or geologically related, like the layers, porosity, permeability, distributions, faults, and rock types. And then there's dynamic probability, which is the relative permeability, capillary pressure, PVT data, fluid contact, and aquifer model. So this is more about the flow simulation model. And they have these models, and what they want to do is history matching. And the reason they want to do history matching is where it's kind of like the stock market, which is if you know and understand the history of how the stock market behaves, it doesn't really tell you much about the future, but it can sort of explain things about the future. So it can allow you to make better decisions about the future, but nothing is absolute, right? So again, it's this world of unknown. It's similar to the stock market in that sense. So what they do with their models is they do this history matching because in theory, it should provide a more accurate prediction of the future or forecasting. So they do this by adjusting uncertain parameters like the permeability, the skin factor, the relative permeability, the fault transmissibility, until the model matches historical production and pressure. And again, they do this because with the hope that if they can adjust the history, or their model matches the history, that it will do a better job or a good job in predicting the future with their forecasting. And then based on the long-term reservoir performance, again, you're talking about 30 to 50 to 60 years or even more than that of production or of a project. So you're planning for that amount of time, right? So you want to predict or forecast the future oil and gas water production rates, the breakthrough times for water and gas, and then the plateau. That's basically when it starts to become uneconomic to maintain this oil reservoir, and when it's time to plug and abandon that well. And also with respect to numerical models or simulation models, if you've never seen one, they basically break up this geological model into these very small blocks, right? These very small blocks, the cubes you can say, and you run a simulation on each cube. And the idea is, depending on the parameters of that certain cube in a grid block, is that you can run the simulation throughout the entire reservoir model. This is like a mathematical method, right? It's called numerical mathematics. And these simulations are basically doing that. And there's very expensive software to be able to do these kind of simulations. And these simulations on forecast, they don't take a short period of time, right? This is a really big calculation, a really big simulation. So these take days or whatever. And then another thing that reservoir engineers take care of is the reservoir management, right? So they're tracking the pressure rates and the well performance. They're identifying which well needs artificial lift, which well needs stimulation, which well needs to become a water injection well. And again, they use these optimization methods that we have discussed before, like the pattern water flood optimization, gas reinjection for pressure support, or CO2 injection, or free refracturing horizontal wells, conformist control like gels and polymers, infill drilling, infill well drilling, and ESPGL installations to maintain flow at low pressures. So all of these are the ones we've talked about, and basically a reservoir engineer needs to know, with respect to the reservoir, how these things are being used, and then based on the recommendations, and then that sort of triggers a change in the model, right? So that changes the forecast, that changes the prediction. So it's this continuous iterative process where you have to tell or go back and reassess, reanalyze, and repredict or reforecast, and then you make a decision and you go back and you continue. So there is this continuous thing for the entire life cycle of the reservoir that you want to maintain and do. Now, when we talk about reservoir engineers, again, all of these things, you'll realize that they're very well related to the economic evaluation, right? Because to maximize the production on using these different methods, they need to make sense in terms of money. So the reservoir engineer will continue to do that with the economic parameter at play until the end of life decisions of a well or a field. So they need to be able to choose, because for example, if CO2 injections are too expensive and no other stimulant will be able to help, then maybe it's time to abandon. If the pressure has dropped beyond a certain point, is it worth it, right? Maybe it's better to abandon. So at some point at the life cycle of a well, an engineer must know when to say it's the end, right? Because at some point you might turn where you're losing money to maintain that well open, right? And at the end of the day, petroleum engineering is all about making it economic and making it profitable. So economic evaluation throughout all of these different methods, throughout all of these different procedures are extremely important, right? Up until the life cycle of a well. And that concludes the life cycle of a well. We're going to now move to petroleum economics, right? So petroleum economics has different fields, and why it ties so greatly is that now we know about hydrocarbons, we know about what properties we need to look for, what properties exist. Now we know in the terms of life cycle of oil how to get all these properties and how to produce the oil till the very end, and we just abandon the well. But the main drive that we've been talking about is that dollar value, is that economic aspect to all of these things. So to talk about petroleum engineering, we must include the economics of petroleum because it's so important. And it allows for us to know when we're profitable and when we're not, right? So when we talk about the entire life cycle of a well, all of these decisions have to be profitable. Now, in the beginning of the life cycle of a well, there's a lot of uncertainty and high risk, and there's no profitability, right? We haven't actually produced anything. So you want to turn this to make money at the end of the day. So when you're making a decision, even at the beginning till the very end, money is a huge factor, profitability is a huge factor, cost is very important to be aware of, right? So all of these things are extremely important. So when it comes to petroleum economics, we want to define some terms here, and within each one of these categories, there will be a few topics that we will discuss. So there are projects, and when we think of it, that's the entire on the field level. When we're talking about a project, there are industry or oil economics associated with at the industry level. There is risk and uncertainty at both the industry and project level that are affected by different topics. There is the different economic analysis one can do to optimize, again, their production at an economic rate. And whenever we say this is just making money, the right amount of money dictated for you to consider this profitable. And then we'll use crude oil as an example or a topic to where we can look at different financial terms that we would expect to see in petroleum economics and different cost types, and then reserves and how to define those reserves, like the map we saw initially in that the world diagram where there's different reserves and what those mean. And then finally the forecasting, which is similar to the reservoir engineering forecasting, but this is on the economic front. And then we'll talk about project evaluation and things like depreciation and depletion and the expected monetary value, right? So we're going to go through all of these topics one by one. So projects are basically, when we're talking about projects, is for a given field, is capital intensive. We're talking about a very long project lifetime. So this is characteristics of a project. Like we mentioned, it will take for primary, secondary, and tertiary recovery about, well over half a century, right? So this is very long, and the uncertainty is very high. So when we talk about projects, we want to be talking about these three subcategories. And capital essentially just translates another word for money. So economic analysis is basically a way that we can, or a tool that we can use in the industry to estimate our cash flows, assess profit loss, and assess investment risks. So it will tell us how we can understand the different risks and the different potential profits that we can make from a given project for a given field or a collection of fields, or from a given country or whatever. It's dependent on the scope of which you're assigned, right? But we want to be able to analyze in an economic sense our projects so we can better understand how much money there is to be made and when it's time to also abandon and close, right? So there's this plateau in terms of profitability that when you realize, in similar to reservoir engineering, where you also have to know when to end a project, right? So start a project, maintain a project, and end a project. These are three different parts where you need to analyze differently and decide differently, right? So for us to get into how petroleum economics work, we must go through different terminologies, right? So there's cash flow, which is money coming in, right? And the money coming in is dependent on the profit you make, So that can translate into uh, the barrels of oil or gas you're producing a day, right? And subtracting it from the expenditure. And expenditure, we can kind of break those down into two. Uh, so there's capital expenditure, also known as capex, or operational expenditure, known as OPEX. And we will define those more thoroughly in the coming slides. But basically, it's different categories of how you categorize your expenses, right? How you define your expenses, and this goes into budget making, financial planning, and it's very important if you're working with banks, if you're working with loans, if you're working with financial like statements and stuff, you need to know how to define your expenses. And then the income estimate is your revenue or your profit, right? So characteristics of the oil and gas world that we should be familiar with, and we already are familiar with it in terms of we've talked about it before, but obviously oil is not a renewable energy. It's not like solar or wind, is that once you take it out and use it, you cannot really use it again, right? So since it's non-renewable, it makes the stakes quite higher. And this long pre-producing period is the period we're talking about where it does cost a lot of money to run surveys, to create the geological models, the geophysical models, the basin maps. This takes time and money, right? So there is there's a long period of time where you are not making money from this project. And the cost is also remains uncertain, even if you kind of have an idea. To give you an example, there was this one reservoir that existed. I forgot the sea, but I believe it's in the Caspian Sea, and they built the rig and everything like that, and they weren't accounting for the sulfur content, and there was a high sulfur content to where they couldn't feasibly drill into it. You know, sulfur is explosive, and I think they spent almost 20 years, and they were still not able to drill into this reservoir due to the fact that of the sulfur content, and they invested so much money to trying to accommodate and modify and to be able to drill into that reservoir, and just due to some unfortunate event they were not able to. So here a lot of money is lost. You're talking millions of dollars are lost, right? So there is this uncertainty that can happen with any project, right? So with the uncertainty of it being completely zero or a dry well, that's really bad, obviously, but there's also the uncertainty that it'll be profitable. So is it worth drilling all these wells? Will it make me my money back and more? And the risks that are associated with oil and gas is geological, economic, engineering, and political. And here this is more than one, right? Like, for example, Macondo is an engineering risk that turned out bad for them. Geological risks is like this sulfur content that I told you. Economic could be, the price of the barrel could crash due to other reasons like war or politics or whatever. Or, like COVID, for example. During COVID, all transportation was kind of cut off, and that's a huge impact on the oil market, right? So that was sort of this geopolitical thing that happened that's impacting the economics of a project and impacting the economics of oil. And political and engineering is where, for example, people that are not trained or people that for whatever reason didn't follow what they were supposed to, they run into this problem, or maybe lack of skill or whatever it is, and they're not able to solve the problem, and they can cost time. So whenever it's engineering, usually you're talking about NPT, which is non-productive time, right? So for example, and sometimes it's not the engineer's fault, right? Lots of the time it's not, but anytime, so for example, in wireline, if your tool gets stuck in pipe, that's like the term they use it, that it's stuck down there, the engineer has to try and find a way to pull it out, right? So there's a lot of problem solving that goes into play, a lot of debugging, you can say, that goes into play. But during that time, the company is not making money. So that's non-productive time, which translates into loss or potential losses, right? So that could be an engineering side of risk or uncertainty, and political. We talked about it usually during war. Like the most recent thing that I can think of, for example, is Russia is one of the main producers of oil. When the Russia-Ukraine war happened, Western Europe did an embargo, forcing Russia or to economically struggle, and then they sold their oil to India and all this. There was like different things, South Africa and stuff. But the idea is that just something simple or non-related to oil and gas can impact your project drastically, right? And that can kind of happen overnight, like and it can happen. And when this happens, is you don't know the time. Like for example, right now the Russia-Ukraine war is going on. In 2003, when the Iraq war took place, it lasted for a very long time, and you don't know at that moment in time when you're working on your project, for example, is this war, is this political influence going to impact me for 6 months? Is it a year and it will be resolved? Is it 2 years? Is it 5 years? Is it 10 years? And when we're talking about these political impacts, like for example, when Saddam Hussein invaded Kuwait and broke off the energy supply or whatever from the U.S. Like that was a war that impacted obviously the oil politics of the world. That was a war over oil, right? So these events in history, and they can happen in the present and will happen in the future, is that these political events can have drastic influences and impacts on projects, current projects, or unstarted projects, right? So it's worth noting that and that remains as an uncertainty, as a risk, right? So if you're going to drill oil in a volatile, you can say, or a politically volatile area, then you run that risk. So risk and uncertainty is just the nature of oil and gas. So it must be within the nature of the petroleum economics, and it must be something that economists or petroleum economists are aware of and take into account when they're working on projects, right? So, like we said, not all wells are producible, and if wells are producible, not all are feasible. And when we say feasible, say not feasibility in terms of the dollar value or in the money value, is that it could not be economic to produce from that well, right? It might not be profitable. And other uncertainties is the expected revenue might not be the reality. So when you make all your forecasts for the project and you're expecting this output, but then the barrels that you're making are the same, but then something drastic changes, like the oil price. So oil price volatility, unforeseen events like environmental or political, etc. So these are things like environmental. We can say something like COVID, or in Texas, for example, if a hurricane comes through and takes down like all these things, is that you have to shut down for weeks or months, and you don't know how. If it floods and it breaks, there are lots of unforeseen events that are completely out of your control, or of the project, or out of control of the economists or even the petroleum engineers, that we sort of just have to deal with if they arise, right? So there's lots of risk, lots of uncertainty, and in the beginning of a project, there's very high risk and very high uncertainty, and throughout the project, economically is the same as sort of as an engineer. What they're doing is they're trying to reduce the risk, reduce the uncertainty, and come to more concrete values in terms of profit, or concrete values in terms of costs, and to have a better idea of what to expect in a given project, right? So the way they do this is they go through this economic evaluation, and what that is that they want to evaluate what the income is, what the expenses are, and how long it's going to take, right? So these are the three variables, you can say, in almost every equation with related to economics, is that we're essentially trying to solve for income and expense for a given period of time, right? So economic evaluation evolves around those three. And the way you do this is that you want to come up with an analysis or a forecast or some economic model that you can define for your project, right? So the steps that you would do this is that you would set your objectives of what you're trying to accomplish, so your success and your failure criterias. You want to formulate different scenarios similar to how a reservoir engineer would formulate those. So that's making predictions for the future, for long term on the project development and how well you can profit from it. And then throughout this, and this is also a continuous thing, but you want to identify the risk and uncertainty, and obviously those change with time, so you're constantly updating and reassessing and reanalyzing, right? And you're collecting all the available data at a given time. So at the beginning of the project, there's certain data you can acquire throughout the project, there's certain data, and then towards the end of a project, there's additional data that can lead you to decide to end the project, right? And when you're doing all this and you're formulating the different scenarios, is that what you do is that you translate that, similar to how a reservoir engineer translates that into a simulation or a simulation model to get outputs. And economists will perform these economic forecasts and calculations to find, based on the different scenarios, what are the expected outputs, what are the expected forecasts, and based on that, they will choose the optimum plan, right? So again, their optimum plan is to make the most money. Making the most money translates into producing the most oil with the least amount of expenses, right? So that's what the analysis covers. And now we can move into what the criteria of a project would be, right? So when we say project criteria, that means is that what are the things that we're looking at that help us make these decisions that we just defined, right, for the optimal decision and so forth. So we'll go to define these in a second, but we have the payout periods, the profit to investment ratio, the present worth net profit, the present worth index, and the discounted cash flow ROI. And when you say ROI, it's return of investment. ROR is rate of return, sorry. So these are just common economic terms or financial terms, and we'll define each one as we go. Some of these are equations or mathematical equations, so we'll look at more in depth when we get to it. So also we want to define what we're looking at, right? So we'll use the crude oil as sort of an example to guide us through all the different terminologies and topics. But with respect to the petroleum economics, is that we want to do all of these things, right? So we want to basically define our project. We want to take into account the different industries we're working with, the risk and uncertainty. We want to do the economic analysis that we just defined, and we want to we'll look at crude oil to define that. So that tells us more about, like, with respect to oil, because there's LNG and other things that we also produce, but crude oil is a good example. It's the most popular example, I guess. And then the different types of costs. What does it mean when we're talking about reserves and forecasting finally, right? So first we want to classify our oil. So in our project, we want to know what we're working with here. And the economic classification is based on these four. So location it's very different, for example, in terms of risk and uncertainty, or because based on regulations of the country or whatever. So if I was in Kuwait versus Saudi Arabia versus Venezuela versus Texas versus North Dakota, they all have their different rules that you have to follow by. They all have their different constraints that you have to take into consideration for the project. So location becomes an important economic parameter. The viscosity of the oil will tell me about the nature of the oil. Is it light? Is it intermediate? Or is it heavy? Sulfur content, like the previous example I said, where high sulfur content is explosive, so it changes the entire project. And when it comes to sulfur content, when it's low sulfur content, we call that oil to be sweet, so sweet oil. And sour oil is when it's sorry, when we have a higher sulfur content. And just to put things into perspective, high sulfur content is anything more than 0.5%. So anything higher than 0.5% sulfur is considered to be called sour. And finally, your API value, right? Your gravity. So if you have a high API, that means you generally will have a high price due to your gasoline. And that's just due to the fact of the refinery process. So when you take if you take like a higher API compared to a lower API and you go through the refinement process, you will find that you kind of get the gasoline wise that you will get more buck for your value or more dollar for your value with higher APIs. So for capital expenditure, we saw this as CapEx. That is basically long-term investments that are required to discover, develop, and produce hydrocarbons. These are large, upfront, non-recurring investments tied to major physical infrastructure and field development. So this is the first category. Usually your CapEx comes in the beginning of the project. You generally don't have CapEx towards the end of the project to the continuation. That translates into operational costs. So examples of capital expenditure are offshore structures, pipelines, well drilling programs, onshore processing facilities. So these are things that you will pay for once and you kind of have them, right? So once you pay for them, you can use them, and that's that. So that's what you can think of as a capital expenditure, is something that I'll pay for once. It's a big expense and I need it, and usually it will last me for its lifetime and for its needed lifetime in terms of my project, right? Whereas project income, so the reason we're going into this is that so before we get into that, actually, let me go back here for a second. Okay, so for capital expenditure, we just defined. So operational expenditure is when we're talking about operational expenses, and that's like, for example, personnel or overhead count or some things that you will be paying within a year and you will reuse it. So it's a reoccurring cost. That's the opposite of capital expenditure. And operational expenses usually last much longer time and they're much lower than a capex expenditure. So these are the two expenditures. So when we've talked about the expenditures, we can move to the income, and the income is you can translate it to oil and gas sales, right? So the oil and gas sales, that's how much money I can essentially make at the end of the day once I produce all that oil. When we're talking about income and we're talking about costs, we need to be familiar with some terms. So one of the most important terms here is inflation, right? And most people are familiar with inflation just due to the fact that we see it in other things, right? We see inflation when when you see the price of milk go up due to inflation, or when you see the price of food go up due to inflation, or where you see less chips in your bag of chips, that's a result of inflation, right? So inflation also impacts oil and gas or petroleum economics, right? So it's the idea of how a price evolves over time and what's the value of your, if you're talking dollars, the value of your dollar at a given time, right? And that sort of fluctuates depending on external factors. Again, this is economic, political, geopolitical, lots of different things. But when we talk about inflation, we usually talk about it in terms of a percentage rate. So 6% inflation, 9% inflation, and positive, generally means that things have become more expensive, prices are rising, cost is higher. Negative means prices are falling. I don't think I've ever seen inflation fall, in my lifetime at least, but in theory, if it's negative, that means prices are falling and things are becoming cheaper in the world. And the equation of inflation is shown here, where I, for inflation, the inflation index is equal to 100 to convert the percent, 1 plus R, and R is the inflation rate per annum, and N is the number of years. And again, there are different equations where you can take the quarterly inflation or the half inflation or whatever, but this is an example of the more common one where it's by year, and you can look at it here. So here the R is per annum, and obviously it would change if you wanted to do it for a different time period. Now, time value of money. This is just a concept that one must be familiar with, and that is the idea that the time value of money is that money value decreases with time, right? And what that means is that my dollar today is worth more to me today than it's worth 5 years from now or 10 years from now. Just due to the fact that things like inflation, things like cost, things like that, is that your dollar depreciates. So that's why people say never leave your money in a bank, right? Or under your mattress. Because if I have $100 today, I can buy, let's say, things like 50 things with $100, right? In 10 years time, I will not be able to buy the same things, right? Like in the 40s, a cup of coffee was a nickel. Now a cup of coffee is like $4 or $5, even $7 if you go to Starbucks. So my dollar today is worth more to me than my same dollar in the future. So that's something we can kind of account for mathematically or economically, but it's just a fundamental concept that you should be aware of. Sorry. So the inflation interest in reverse. Here is the equation of the present value. You will use present value a lot because the net present value of a project is extremely important. But present value PV is equal to 1 over 1 plus d raised to the n, where d is the discount rate, and n is the number of years, and v is your value in n years, right? So that will tell me the present value of something I have. And the net present value, which is the most common financial method or economic method that you take or you always want to have, it just assigns a present worth for a long-term project that will yield either your profits or losses in the future, right? So it's trying to understand what is the present value so what is the present profit of that project after 10 years or 5 years or so forth. And the way you do that is that you sum all the incremental present values, and that will give you the net present value of your project, right? And why do we get net present value? Well, it tells us a lot, because when we see over here in this visual, the optimum abandonment, for example, so when do we plug and abandon our wells, or when do we stop our project, is money driven. It's economically driven, right? So in this case, the NPVs over whatever years is that you can see that there's this optimal point where it starts to decrease again, right? So as an project economist for petroleum, is that you want to maximize the NPV, right? And you need to know when you're starting to lose money. So that's something to keep in mind, is that over time, right, your NPV will kind of have this parabolic structure, and you kind of want to go out when it's optimal or when it's most optimal for you to make money and not take any costs, or costs outweigh the profits, right? So that's why NPV is very important. Now we'll move on to additional economic measures or economic calculations. So there is the net value, payback time or payout time, the rate of return, like we discussed, is ROR, the profit investment ratio, the present value profit ratio, the growth rate of return, and the internal rate of return, right? And where we said rate of return is ROR. So in terms of the economic measures, before we get into the details of which one is which, is that some consider time, the time value, and some do not consider time value. But all of them are equally, or not equally, but all of them are important to calculate, because they tell you different characteristics of your project and they answer different questions. So the payout and the cost to find reserves and the cost to develop reserves do not take time into consideration or in their equations. And the ones that, I mean, they do consider time value, sorry, and the ones that do not consider is like the net present value, the rate of return, and the net cash flow. So payout time basically is when you take all your expenses, your initial investment, operational expenditures, your capex, your taxes, and then you take your net cash flow, and it is the time it takes for your net cash flow to turn positive, right? Because at the beginning of the project, you're basically spending, and there's no profit, and then at some point, you'll start to profit, and you haven't made up all your debt yet, and there's a point in time where you will have a net cash flow that will go to zero, and the second it starts to become positive, that is when you've paid out your expenses and you can move to a positive net cash flow, and that is what the payout or payback period time is. The rate of return, or the ROI, is when the net present value equals zero. And the equation for it is the summation of all of the net cash flows over 1 plus I subscript R, and that's basically the real discount rate, and K is the time period. So you set that equation to zero, and that when you solve for that, you will know when the rate of return is, right? The discounted profit to investment ratio is also known as DPI, is a ratio of NPV to the PV investment. PV of investment is also depicted or denoted as IPV, which is basically the sum of all the investments, where 1 plus I raised to the K, same terminology as before. Another term is the discounted profitability index, where you take your DPI, again it's also depicted as BI, but here you're taking different values, where you take the present value over the IPV plus 1, and this will tell you the following. So if the DPI is greater than 1, you have a profitable project. This is a good project to have. If your NPV is less than 1, obviously then your project is going to get rejected, because that just means you're losing money. And if NPV would equal to 1, in reality, this would also get rejected, but it means that your project will just make you back the money that you've invested, which is not really a good decision, right, in terms of economics. But these are good indicators, or the categories where you can draw the lines. So the next step is to know which measure to use as an economist or a petroleum economist. So the necessary investment, you need to use screening criteria. And what do we mean by screening criteria? It's the NPV and the internal ROR, rate of return. For discretionary investment, use ranking criteria, which is the discounted ROI and the payout time. And this is just based on when you're trying to get a project on board, when you're trying to propose a project. These are the different things that you want to use depending on the scenario you're in, right? But the overall economic goal is optimization. Like everything else in petroleum, is that you optimize. But here, what do we mean by optimize? So in the petroleum engineering world, optimization means to maximize oil production and maximize your safety, and reducing uncertainty and reducing risk. When it comes to the economic aspect of petroleum, you want to reduce capex, you want to reduce opex, you want to reduce your costs, basically, your indirect costs. You want to delay expenditure, so that means basically avoid spending money at all costs, right? And you want to increase your income as much as possible, and you want to improve your project value, and you want to accelerate your income. So the faster the money comes, the more freedom you have, right? So with that in mind, we can talk about a few more terms. So here, depreciation is similar. People use this also a lot with respect to inflation and depreciation. but it is the concept that a non-cash expense that spreads the capital cost of a tangible asset across the periods in which it provides economic benefit. So the best way to think of a depreciation is like when you buy a car. If you buy a car and you use it for 6 years, or maybe it depreciates, right? Is that it will benefit you, but it's losing its value every year. So almost anything you buy or anything you initially invest in, like this non-cash expense, is that it's this cost that you will benefit from, but each year it depreciates by 5% or 10% or so. And you can calculate depreciation in multiple different ways. And we'll talk about the different methods you can calculate right now that are commonly used when it comes to petroleum projects. So there's the straight line method, the decline method or decline bounce method, double decline, sum of the year, and the sinking fund. Okay, so the straight line method, it spreads the asset's costs evenly over its useful life. The same amount is expensed each year, and the formula is just the annual depreciation is equal to the cost minus salvage value divided by the useful life time period, right? So this is one of the most common methods to calculate depreciation. It's very simple, it's predictable, it's good for planning. You know, we like simple, we like to be able to predict things on the go. And it's best when the asset wears out uniformly over time, right? So something that sort of decreases in value linearly or is worn off linearly, we can sort of use this straight line method, right? Then the decline method or the decline balance method, it's the accelerated method that applies a constant percentage to the asset's remaining book value each year. Depreciation is higher in early years and lower later. Depreciation is equal to the book value at the start of the year multiplied by the rate, where the rate is equal to 1 over the useful life period. And this is used for when an asset loses value a lot faster in the early years and then sort of slows down later. So this is commoner for machinery or equipment, right? The double decline method is also very similar, but you're just multiplying by 2. And this is for declining balance, where the depreciation rate is double the straight line rate. And the reason you would use this is because it has a much higher depreciation in the early years. So you kind of are pushing that magnitude by 2, right? And it never depreciates below the salvage value. And you switch to so you want to use this in the beginning, and then you can switch to another method or the straight line method. So it's like initial spike of depreciation, and then it continues linearly. And this is used for assets that rapidly lose efficiency or value, like drilling rigs, pumps, or vehicles. That's a very good example of something that where you would want to use the double decline method. The sum of the year is another accelerated method that assigns a higher depreciation cost in early years using a weighted fraction. And basically how it works is that you compute the sum of the digits of the asset's lifespan. So if you had a 5-year asset, you would do 5 plus 4 plus 3 plus 2 plus 1. And then each year's depreciation would equal the remaining life divided by the sum of digits multiplied by the cost minus the salvage, right? And this is used for assets that generate more value earlier in life. So equipment with high initial output, right? So you can think of different equipment in the petroleum field where the initial output would be much higher, and then it depreciates over time, right? So you would use the sum of the year method. And finally, the last method is that you would use is the sinking fund, which is depreciation that is calculated based on the amount you must set aside each year earning interest. So at the end of the asset's life, you have enough money to replace it. So the annual depreciation is equal to the cost minus salvage multiplied by I divided by 1 plus I raised to the n minus 1. And here I is the interest rate and n is the useful life, right? So a small depreciation early increases each year. This is the only method discussed here that includes interest, so the interest earned, and it's really used for financial planning for asset replacement, like utility companies, long life infrastructure, etc. So these are just different depreciation methods. Lots of them are used in the petroleum and economics world, but these are different examples that you might be able to relate to, right? And finally, for part one, we can talk about the project risk and uncertainty. This is the last topic of the petroleum economics, but uh, in the world of a project, you must realize or recognize the truth that there is more than one possible or probable outcome that can happen. So even if you select a given outcome, that kind of spreads into this tree-like diagram, as you can see here, with below in the image. And this is because of technical, economic, and political losses or situation that can incur losses. So you want to be able to accommodate to the best of your knowledge with all of these. And what economists do is that they do these decision trees, how they break up financially based on percentages and different scenarios on where they would end up, and then you want to pick the most optimal one. But that's how they calculate risk and uncertainty, right? So that concludes part one of this lecture. Part two, we'll be talking more about different topics in the petroleum, also high level as we've seen so far.